Okay. Last time we kind of talked about complex topicalization. And we applied this complex topicalization to kind of construct simple examples tropical curves. So essentially we take curves over C, complex numbers, and kind of tropicalize them. And the result that we got, so we constructed several examples, but kind of the most relevant example was kind of line in P2. So that was tropical line in P2. So essentially we had an equation y plus x minus so that was equation with homogeneous coordinates. Coordinates in P2. And after performing complex tropicalization for variables x, y, and z, and tropical constants a and b, so that was our kind of resulting tropical curve. And then we kind of discussed some features of this tropical curve. Okay, so there are like three types of features. So there are these kind of points at infinity, or points where our tropical curve crosses these compactified hypersurfaces for projective space. And kind of we discussed details like the structure of the tropical curve in these regions. So in kind of orange region, orange region, so we essentially observed that the tropical, okay, so in the general region, tropical curve is essentially aligned with the circle fiber over this, and this circle is embedded inside of two-dimensional torus, and this embedding is controlled by assigning kind of integer vector. So by assigning homology class of this circle, so this integer vector that belongs to Z2. So therefore, for each kind of edge of our tropical curve, we have an integer vector assigned, and furthermore, this integer vector, it kind of controls the slope of this tropical curve. So we can kind of describe this edge as a parametric embedding, so with just some vector as a function of parameter t along this edge, and kind of the rate at which this vector changes exactly equals to m, which is the same m as homology class of the curve. So that was kind of structure of a curve in a generic point. So kind of for generic point or generic tiny neighborhood of inside of this edge, we basically have like constant slope in radial direction and some fixed homology class, and kind of the change of angular variable with respect to some kind of other angular variable phi is also given by the same. Okay, so then near kind of this edge points or near points at infinity, or kind of in regions where these edges go to infinity. So we essentially observe with the following property that for this external edges, so for external edges like ME should be equal to a normal vector, and that is a normal vector kind of hyperplane which intersects this edge of infinity. And due to this property, essentially the structure of a circle vibration over this semi-infinite edge has this kind of structure of a cap. So away from this compactifying hyperplane, the circle just has some finite size. But then, as we approach this compactifying hyperplane, the size of the circle goes to 0, and essentially the structure of our tropical curve near this compactifying hyperplane looks like a cap. So it's a circle that shrinks to a point. So that is structure in this yellow region, and then the last region is red region. So red region was the region that was the region near cubical vertex, and once again, so over each internal point of this triangle, we have a two-dimensional torus fiber over it, and then in this junction point, we essentially have like 3 different edges meeting. So we have like M1, M2, and M3. So they are kind of slope vectors, the same, and which are the same as homology class of the corresponding circles. And then the structure of a tropical curve near this junction point looks like a pair of pens. So it's kind of like a 3 circles on a torus that kind of undergo some smooth junction. And then by studying, by observing that homology classes of these 3 circles, M1 and 2, and so that these 3 circles kind of with some proper orientation, they form a boundary of this pair of pens. This union of the circles, let me label them M1, M2, and M3. Disjoint union. And then, because boundary of the boundary is 0, so that implies, and our embedding is smooth, so that implies that such embedding is possible if and only if the sum of these homology classes is 0. And that is this additional property that kind of, okay, so here let me be more careful. So this is some orientation. So orient sum of this 3 integer vectors should be 0, and that's exactly what happened in our examples. Like in this example, like if you choose our orientation, say like this, and like this, so then we have 3 vectors, 1, 0. So that is slope vector for this curve. So here 0, 1, slope vector for this vertical edge, and then the slope vector for this edge should be 1, 1, so the edge goes 45 degrees, and indeed the sum of these 2 vectors equals to the third vector. So that was kind of structure of a tropical curves that we observed by studying some examples, and kind of we started with examples in complex plane and then compactified it to CP2, and then furthermore we studied kind of degree 2 curves. Curves in CP2. So, and our main tool for studying these curves was to start with kind of the curve that is how to say, okay, the composable. So it's a curve that is a variety that is 0 locus of a product of 2 polynomials, So we started with a 1 degree 2 curve, degree 1 curve, and then another degree 1 curve. So that gives us a kind of reducible degree 2 curve. So that is reducible. So reducible in a sense that degree 2 polynomial is kind of a product of 2 degree 1 polynomials. And then what we did, we said that here we have some kind of valence 4 vertex. And we say that valence 4 vertex, so generally valence, okay, vertices whose valence like more than 3, which is 4 and higher, so that is kind of tropically non-smooth. And we need to kind of deform it to get kind of multiple valence 3 vertices and additional edges. To get kind of smooth tropical curve. So in this particular example, kind of resolution. Okay, so this deformation is not unique. In the case of 4 valent vertices, so there are okay. In the case of 4 valent vertices created by intersection of 2 lines, so there are exactly 2 resolutions. So in this case, still draw it in white. Draw one resolution. Okay, sorry. This, so go with this, and here white. This, yellow. So that is kind of one resolution. So we essentially resolve it this cross into this object. So we kind of split this 1 4-valent vertex into 2 3-valent vertices, and we inserted this additional red edge. So that is kind of one resolution. So there is kind of another possible resolution when we resolve it like this. So that is kind of another resolution. And the tropical curve that we get if we apply second resolution would go like this edge continues here, this edge continues here, like this, and then these two. So here you can clearly see that these two are distinct. So they are two distinct trees with split leaves. So we can kind of redraw. So here we have like two distinct trees embedded in some particular way. But let me kind of just draw a topology of these two trees. So the topology of this tree looks like this. So that is these two edges, and that is these two leaves, and two leaves are kind of attached in the middle. While the topology of this tree looks very different. So we start with this trivalent vertex, and then each of the internal edges kind of splits into 3 leaves. So they are kind of 2 distinct trees with 6 leaves, and they even have like distinct different like symmetry group. So for this one, the symmetry group has a size which is 6 because of the symmetry around this vertex, and 2 cubed because we can flip these external edges. So that gives us dimension of this symmetry group 48. So that is dimension of automotive group for the gamma 2. And here, if you compute the dimension of the automorphism group for gamma 1, then we would get different numbers, so we can flip these 2 leaves, so that gives us 2 square. And then the only other automorphism is that we can reflect this tree, so that will give us total size of automorphism group 8. So they are two distinct trees, and hence they are 2 distinct tropical curves. Because tropical curve is essentially a tree with additional kind of coloring of its edges by some integer vectors that are responsible for slopes of the embedding, and that they are responsible for homology class of the circles kind of fibered over the corresponding edges. Okay, subject to some constraints like this constraint for each vertex and kind of this additional constraints for each semi-infinite edge. Okay. Let me switch to the red one. Okay, so now now before we will go to kind of formal definition, let us talk about a few more features of our tropical curves. So first of all, at the very end of last class, there was a question so for algebraic curves, in P2, so that is kind of 0 locus of some degree D polynomial, degree D homogeneous polynomial in 3 variables. So that was our algebraic curve of degree D. So we have this kind of nice result from algebraic geometry. I'm not sure. Maybe it is actually a theorem from algebraic geometry. The kind of genus of this curve. So for a generic curve of degree D, so genus of this curve is D minus 1, D minus 2 over 2. And then we can kind of, if we include degenerate curves, so including degenerate so then this equality became inequality, so it means the genus is at most this one. So, and this inequality in practice allows us to kind of talk about rational curves of degree D. Remark. So this kind of inclusion of degenerate curves allows to talk about rational curves of degree D, which is kind of subject to kind of Kontsevich-Manin counting, where we count a rational curve, number of rational curves in P2, passing through number of rational curves of degree D in P2, passing through 3D minus 1 point. Okay, so now the question is like whether we see the kind of the similar result for a tropical curve. And what about tropical curves? Okay, so far we only talked. So in our examples, we had like D equals 1 or 2, and D equals 1 or 2 is kind of a case where genus, even in complex case, is always at most 0. So all kind of degree 1 and degree 2 curves are rational. So therefore, the most interesting case of D equals 3 is where D of 3 could be equal to 1. So that's kind of the case. We can have a curve with topology of a torus. Okay, so let us kind of try to repeat our approach. So D equals 2 tropical curves. So once again, now we will start with degenerate. With reducible tropical curves. So once again, we start with reducible. So our degree 3 polynomial is like a product of 3 degree 1 polynomials, which we will draw, and we will draw the zero locus of this 3 polynomial in tropical setting by 3 different colors. Picture like this. So for another polynomial, we have a picture like this, and we have a picture like this. So now here we see kind of key property. So we observe that degree 3 reducible tropical curve is a graph with one loop. So let me use red color, kind of outline this. So the topology of this graph is such that it has a. So now the natural question is that, okay, so even though it is kind of valid reducible tropical curve, but we agreed that having the vertices of higher valence kind of gives us a curve that is non-smooth. So before kind of claiming victory that we reproduce this familiar result from complex geometry, we need to deform this tropical curve into smooth tropical curve. And in this particular case, the kind of non-smoothness is sort of attached to our loop. So let me zoom in into this region. So that's a region which contains all 4 valent vertices. So we have these 4 valent vertices that are vertices of this square, which is a loop. And then what we can do, we can resolve these vertices one by one. So there are multiple ways of doing it. Yeah, let me see what is the best way of doing it. Sorry, not all of them for one country. My bad. Let's redraw this picture. So among these vertices, only 3 are for one vertex. So let me redraw it. So it's this one, this one, this one, and this one is kind of all good 3-valent vertex. So we need to resolve only this. And then we can resolve it by kind of constructing suspension of square. So what we do, kind of redraw our square. We redraw this H, which is H attached to 3-valent vertex, and then for these 4-valent vertices, we just kind of introduce a tiny internal edges like this, and we store our remaining 6 edges. So in a sense that previously it was kind of a square that is kind of rigidly attached to these 7 edges, and now we kind of inserted some additional red edges to kind of suspend this square inside of the 7 edges. So now we kind of resolved everything, and after resolution we still have so after deformation. So we have a smooth tropical curve. After deformation, smooth tropical curve. In the sense that all vertices are 3-valent vertices, and the corresponding graph, while graph U has one. So this book here, it kind of resolved under resolution. So now there is kind of immediate question, like, is it true in general that resolution preserves the number of loops, or I was just kind of lucky and used some special resolution? Because like here we saw that resolution is non-unique, so we can resolve our 4-valent vertices in a different ways. So maybe if I resolve this, and here I resolve in like 3 4-valent vertices, so that should give me 8 different ways of resolution. So maybe I was lucky with one particular choice of 8, and with other choices I would get like a graph with smaller or larger number of loops. So let us prove lemma that resolution preserves the number of loops so it means that L of gamma equals to L of gamma tilde. So resolution gamma tilde preserves the number of loops of gamma. Namely, L of gamma tilde equals to L of gamma. Okay, well now I can. Okay, I still want to keep this one before we prove general state. Six. Okay, so kind of proof of the lemma. Okay, so in our proof, we will do two things. That resolution of higher valence vertex, okay, valence equal to n, could be done in n minus 3 steps of so n minus 3 steps of introducing one internal edge per step. So essentially we have like a vertex with very high valence, and then we will resolve it. Okay, maybe it's kind of too much. Maybe it's okay. Yeah, let's do just 6. So vertex of valence 6, and then we resolve it in steps. In three steps according to this thing. So first we say introduce one internal edge and keep and kind of valence of this vertex. So original valence was 6. So now after we resolve it, we get two vertices. This kind of v1 is 4, and v2 is 4, and we have like number of internal edges equal to 1. So here there was no internal edges, so no internal edges and 6 valent vertex. So after resolution became pair of 4 valent vertices and one internal edge. And then on next step, we once again take one of the vertices. So they are still 4 valent vertices, so we need to further resolve them. Let's take say this vertex. So we have h like this, and something like h like this, and this two, and here is still something like this. So let me denote this e1, internal h e1, e1, and e2. So now we have three vertices with valence. Okay, so v1 is still 4. Okay, let's use this notation for valence of vertex, and let me label. So then vertex v2 is a root vertex, so it has valence 3, and then vertex v3 is also good vertex, it has vertex. So our tropical curve is kind of smooth in vertices v2 and v3, and still kind of non-smooth in the vertex v1, and that's kind of where we kind of take step 3. So here, like, initial n was 6, so 3 steps, and then here we resolve draw it e1, and let me draw it something like this. Let's see, 2. Yeah, okay, and here total number of internal edges is 2. So our internal edge. Okay, let me also, since I'm going to introduce this notation later, so this E of gamma is kind of a set that consists of one internal vertex, and here E of gamma tilde, gamma tilde, so E of gamma double tilde consists of 2 internal vertices, and the cardinality of this set of 2 internal vertices. And here, similarly, so all vertices have kind of valence 3, so P1 to 4. So we have 4 vertices of valence 3. Okay, here number of vertices is 1, and here V of gamma triple tilde. And now we have 4 vertices of level 3, and that we have 3 internal edges. So kind of the cardinality of this set of internal edges is okay. So that's kind of how we in practice carry our resolution process. That we kind of go step by step. So on each step we introduce one internal edge and then split our higher valence vertex into 2 vertices of smaller valences. Okay, so therefore, kind of to summarize, at each resolution step, we do 2 things. So we add one internal edge, and we split our vertex into 2 vertices. So we can split vertex into 2. Okay, so that was kind of explicit description of this resolution, generalized to kind of resolution of any type of vertex, any type of graphs. And we need to do it as many steps as we need till we reach all vertices, till valence of all vertices would reach 3. And we see that at each step, the kind of the valence of a vertex would non-increase. That here valence was 6, at each step the excess of the valence, excess of the valence, so valence minus 3 would decrease by 1. So here excess valence was 3, and here we have 2 vertices each with excess valence 1. So the total excess valence is 2, and then on the next step we only have one vertex with excess valence 1. So and one more resolution gives us 0 excess valence. So that kind of ensures that our process would stop after finitely many times, because at each step in such process we kind of decrease excess valence by 1. And initial graph has some finite excess valence. Okay, so now let us kind of see what happens to the number of loops as we perform this. So let us recall formula. Maybe it's actually Euler's formula. Formula. So if you have kind of graph gamma, which is connected graph, so then the number of loops in gamma we can calculate in the following way. So we can calculate it knowing number of edges in gamma. So let me draw it like this. So E of gamma would be a set that contains all edges, and then this vertical lines would say cardinality of the set. So it's number of edges. And using number of vertices, that is number of vertices. Okay, and maybe plus some additional constant. So that is general structure of this formula, and we can restore like relative coefficients by looking into some examples. So we can start with a tree. So that is kind of obviously a tree. With gamma is 0, and we have kind of two vertices and one edge. So then we can do the following thing. So we can keep a number of vertices fixed and say add one more edge. So L of gamma 2 is obviously 1. So this graph has one loop. So and we can didn't change the number of vertices, but added the number of edges by 1. So therefore here we have just +1. So then we can kind of play this game again. That if I say add the vertex here, it doesn't change the number of loops, but it kind of increases the number of vertices and number of edges by 1. So therefore here the kind of relative coefficient should be -1 between vertices and edges, and here to match this formula, when we have 1 edge and 2 vertices, so here should be +. So that is a formula that gives us number of loops in a graph gamma from counting number of edges, number of vertices, and adding +1. So now let us kind of recall the change in a graph as we perform resolution. So during resolution, so each resolution step so what it does, so it increases number of vertices. So it increases number of vertices by 1. So we split this vertex with higher valence with higher excess valence to pair of vertices with a smaller total excess valence. And we increase the total number of edges by introducing additional edge. We also increase it by exactly 1. And therefore, using our formula, we see that delta L of gamma, which is L of gamma tilde minus L of gamma, like changing number of loops during resolution process, we see that this thing exactly 0 because we increase the number of edges by 1, but we also simultaneously increase the number of vertices by 1. So this difference remains the same. And that kind of completes our proof of this lemma that the resolution preserves the number of loops. So therefore, regardless how we do this resolution, so for any of 8 types of this resolution for degree 3 curve, we would still achieve a graph with a single.
Excuse me.
Yeah.
Why we not prove this theorem by resolution preserves the homotopy type?
Okay, you can do it like this. I just wanted to kind of give you some kind of introduction into counting on graphs, because I think later today we will use this counting formulas a lot. So I wanted to kind of start exposing you to them like earlier. So that was the only reason to go over this longer proof. So now here in kind of complex geometry case, we have this second statement that if you include degenerate curves, we can have a smaller change. Unfortunately, I erased that picture, but maybe I can restore it. So if we do the following thing, so we first start with reducible degree 2 tropical curve, and then resolve it into what? Into something. So that was something like this. Yeah, so we resolved it. Okay, so we have a tropical curve. No, for this one, let me take different resolution. So let's resolve it into okay. Let me kind of sneak peek into my notes. Okay, let me. Bigger. So that was kind of this other resolution. Okay, and let us so that is the tropical curve which is zero locus of some degree 2 polynomial. And let us look at a degree 3 curve which is reducible, which is the product of degree 2 polynomial that describes this curve and another degree 1 polynomial that describes a yellow tropical curve, and we draw this yellow tropical curve like this. So then once again get singular tropical curve. So we do a resolution. And after this resolution of this covalent vertex, so what will we get? What would we get? So it's this part, and here in resolution, let us resolve it into something like this. And here I still have something like this. So this one goes here. Okay, let me specify what was the yellow part. Yellow part. Resolution, and here it still goes less. Okay, so we performed resolution, and here we observed that what we got, that the term of gamma has no loops. That this graph gamma is indeed a tree. So no loops means that the kind of genus of this tropical curve is just zero. So that kind of gives us an example of genus zero tropical curve. And here there are several important remarks. So remark one is that this genus zero curve in a complex geometry setting was something with a singular point. So in complex geometry setting, so genus V, genus like cubical curve of genus zero had kind of singular point. So topologically it looked like some kind of torus whose kind of one of the cycles shrank into a point. So that was kind of our singular point. So while in a tropical setting, this curve looks perfectly smooth. Tropical setting. So that is kind of some important feature of this tropicalization process, that doing this kind of scaling, it allows us to smoothen out certain singularities and treat rational curves of any degree as just kind of graphs which doesn't have like loops. So both like degree zero, genus zero curve, genus zero degree 3 curve, and another curve that we got here by resolution, genus 1 degree 3 curve. So from point of view of graph, they look like perfectly fine, perfectly smooth tropical curves, and they just represent a graph with slightly different number of edges and vertices to accommodate for a different number of loops. Okay, so then there is a second remark. So second remark is kind of here, going from genus 1 curve, which is kind of generic point in the modular space, to this singular point, means that we are kind of performing some, I don't know, some deformation of our curve or some kind of motion on a model. And this deformation, so deformation, or let's call it Chilus reducing deformation. Deformation, it kind of has a very natural interpretation in terms of a tropical curve. So let us once again look at kind of this essential part, which is a part of a tropical curve of degree 3, which kind of contain our loop. So this essential part, it looks like this. Okay, so we can even forget about this thing. Just look at kind of suspended square. So it looks like a square that is suspended on four kind of four ropes. So now what we can do, we can imagine the following deformation. So we can kind of change the size of a square. So this square has moduli which is size. So here what we do, we didn't change the slopes of these curves. So because the slopes are kind of subject to some constraints, but what we can do, we can keep the slopes of all curves, but still decrease the size of a square. So let me draw kind of original square. So that was kind of original square. And what we do, we just kind of slide these four vertices along this directions. And then what we see is that eventually by sliding all the way, the square at some point would just shrink to a point, and what would we get? We would get kind of just four valent vertex. And then what we can do, we can resolve it. Oh, sorry, deform four valent vertex into I don't know, something like this. So we started with this kind of piece of the curve that contains this essential loop, and then we just kind of used the fact that this loop has a moduli which is size of this square. So we deformed it decreases the size of this square all the way to a point, and then we resolved this point into a pair of three valent vertices, and that kind of beginning point of a process that we have a kind of a graph with a one loop and the end point of the process. So we have a graph with kind of the same four external edges, but now without a loop. And we can kind of perform this process with any loop. So and that process that allows you starting from a graph with say L loops, you can repeat this process for each loop to get the number of loops all the way to 0. So by performing this process multiple times, you can get a kind of a tree from any graph. So that is essentially like how we can kind of degenerate. This is kind of tropical analog of degenerating degree D curve all the way to rational curve. Okay, so that kind of explains how we explain this kind of inequality in the case of degree 3. So we kind of constructed an example for degree 3 where genus is 0. And in general, we described this idea of kind of shrinking this loop all the way to a point and then deform a point to some number of three valent vertices, and hence effectively decreasing genus. Okay, so now kind of final step to kind of complete this discussion of okay, so to complete this tropical discussion of this nice formula from so kind of as long as we can achieve as long as we can show that the genus of degree d curve in general is this number, we can get a curve with a lower genus by performing this kind of loop reduction procedure. So now, and the best way to prove this formula, and that is what is nice about tropical geometry, so kind of tropical proof, is just by drawing a picture. So we have our lemma that the deformation preserves the number of loops. So therefore, kind of the best way is to just to draw a tropical curve that is not smooth, but has kind of required number of loops. So and the proof is kind of by suction in degree t. And let me just kind of illustrate how it works, and then the proof will be clear. So let me start with let me start like this. So with my curve of degree 1. So then my curve of degree 2, like reducible curve, is just kind of a union of two curves of degree 1. So here, like I still have no loops, and that agrees with our formula. So now, if I draw one more curve of degree 1, I got my first loop. So so the loop is the boundary of some area. So let me just kind of indicate this area. So I added one more degree 1 curve, and I got my first loop. Let me label it 1. So now, if I repeat this process, so if I draw, add one more degree 1 curve, so bring in a total degree to 4, so then I see that that introduction of this red line, it kind of gives me two more loops, like loop 2 and loop 3. And that's kind of where induction works. That kind of G max of D plus 1 is what with G max of D. So that's kind of the number of loops that we had before, adding one more degree 1 curve, plus an additional loops that we get, and how many loops we got. So the number of loops would be essentially determined by kind of how many horizontal lines we cross. So in particular here, in order to get one more loop, we need to cross. So the number of loops would be d minus 2. So here, let us check. So for d minus 1. Let's see. So we have degree 2 thing, and to have a first loop, d minus 1. And then we have like G max for degree 2 is 0, and then from here we see that this formula kind of solves this induction. So G max, or we can just solve this thing to see that at each step we increase our function linearly. So the function should be some kind of quadratic polynomial, and then we can just plug in our kind of generic ansatz for quadratic polynomial in D, and see that it's indeed given by this one. Okay, so that kind of a tropical proof of this statement from algebraic geometry. So in a tropical case, the proof is just by drawing some simple picture. So, which is kind of one of the advantages of doing tropical geometry is that certain results in algebraic geometry became just the proof of certain results is just equivalent to drawing some smart pictures and relying on some general results like that resolution doesn't change the things and we can shrink some of the loops to a point. Okay, I think now it's a good point to make a break. So now it's 10:57. So let us make a break to 11:05. And then after the break, we will talk about degree of the curve in a more general setting, like how the degree of the curve is related to properties of a graph. And we will also talk, and then we will talk about modeling of tropical curves and dimension of the modeling. Okay. Yeah.
Sorry, maybe because I missed the last lecture. I missed the vertex theorem lecture last time, so I still confused with the relation between the genus of the tropical curve and the genus of the complex curve.
Okay.
In this case, you mean this curve is correspondence which one?
No, so kind of tropical curve, essentially to see kind of topology of a complex curve, you need to imagine that there is a kind of a tiny circle fibered over it. So then if we have a circle fibered over tree, so that essentially from topological perspective looks like a collection of some points, for trivalent vertices, some cylinders. So and some counts. So if kind of circle fiber over tree, then it is essentially a slicing of a sphere in some fancy way. So now if I have say a loop in my graph and I have a circle fiber over loop, so then the picture looks like this. So I still have like a pair of pants. So it's like this, and pair of pants like this, and here is once again pair of pants like this, and when you glue them together, you basically see that there is a torus. So that this thing is equivalent to a picture when we have a torus and kind of 4 tubes attached to this top. So and that gives me a kind of sort of topological proof that the genus of the curve is related to number of loops. That kind of circle fibered over each loop will give me a kind of generator of homology class for a curve.
What happened for this valence 4?
So valence 4 is just kind of analog of a sphere with sort of 4 tubes attached to it. So we can look at kind of pair of pants as a sphere with 3 tubes attached to it. So and higher valence vertex is like you take a sphere, you cut like number of disks equal to valence of this vertex and glue kind of cylinders to each of the boundary of this. And then kind of deformation of a tropical curve is you kind of deform the sphere into something like this. So and then you still have like 2 tubes attached to it and this kind of a cylinder that emerges in deformation of a sphere with precisely this red edge that emerges in our resolution. So here there is kind of no change of genus from kind of 2-dimensional topology perspective.
Why we say this is singular?
So that kind of from tropical perspective it is so it is kind of tropically singular. So so from kind of complex geometry, there is no singularity in this thing. But from a tropical geometry, kind of people call it singular. Or so they kind of want to say that kind of smooth tropical curve is a graph with all vertices being trivalent vertices. So and kind of rest other graphs with vertices of other valence, they kind of want to call like tropically singular. But I agree that there is absolutely nothing special. If you recall that there are like circles fibered over it, then there is perfectly fine junction of any number of circles inside of a torus. So that looks smooth from two-dimensional topology.
This is the defining equation for the complex.
Yes. So we kind of, like on previous lecture, in order to get these pictures, we started with this kind of equation over complex numbers, like homogeneous equation in three variables of certain degree, and then we performed this exponential parameterization for variables and coefficients, and then taken like a certain limit, and here we plotted like radial part, which is kind of magnitude of these two complex variables out, which are like okay. So we kind of draw it in the local C2 chart, covering like part of P2. So that's what we did last time. So therefore last time we have like this procedure of how we go from kind of algebraic equation to a picture, and if we have like algebraic equation that is a product of two polynomials, so that is the same as kind of literally saying that our new picture will be union of two pictures, like one picture for each component in this product. So very much like reducible curve in a complex geometry.
Excuse me, but we do not tropicalize this P2 times P. Because
no, but we separately tropicalized P2 and tropicalized P1.
And take union. We do not do.
Yeah. So we start with kind of in a complex geometry, it is a union of two curves, and then we tropicalize each of the curve, and then kind of result will be union of two tropicalized curves.
This is my confused. In complex geometry, this means they have two irreducible components and they have the singularity.
Yes.
It's just the degree 2 P1 and P1 the union, and we will get two singularity in this picture. But we don't have any singularity.
Oh, no, we still have like this higher valent vertex. So there is some kind of remnant which is tropical singularity, which is this higher valent vertex, which inevitably appears if you intersect like two edges. So each of the tropical curves is a graph with some edges, and therefore union of two tropical curves in a general position would be a situation when some edges intersect, and intersecting edges would naturally give you vertices of valence 4. So that's why, in a sense, kind of tropical curves also like the singularities that appear in a tropical reducible curve, tropical singularities, they kind of appear at the same points as singularities for reducible curve in a complex geometry. This higher valence vertex, they exactly appear when the locuses of these two polynomials intersect.
Maybe you mean this resolution should come with correspondence state. And we will from this to get this.
Yes, something along this line. So I'm not kind of 100% sure, but it's kind of possible that we have like two singular points and for reducible one, and then we resolve one and get only one singular.
Okay.
Excuse me. It's different from we take tropical product of P2 times P1.
Yeah. So here product is like product over like polynomial in a ring of polynomials. So here like P1 and P2 are elements of polynomial ring, and we multiply them as polynomials. So
Yeah, but in degree 1 case, we expect it to be tropicalized, like.
yeah, then we tropicalize each of the polynomials. So
Yes. So why don't this operation commute? I mean, like in degree 2 case, it becomes union, not tropicalized product.
okay, so I think like if you carefully study, so here I'm kind of specifically avoided talking about varieties over tropical numbers. So that's what you normally would do. Say that you have tropical numbers. Let us study varieties of tropical numbers. So that's kind of where tropical polynomial vanish. So this thing, this approach, first of all, it is written in many textbooks, and that's how usually people describe tropical curves. However, this approach, even though it has this advantage that it's more uniform with algebraic geometry approach, where you kind of first introduce your ring and then you study like varieties over this ring. However, it has some disadvantages that in that approach you completely miss a kind of circle and a torus part. So in this approach, kind of people work over real tropical numbers, and all their pictures, their kind of pictures, their varieties over kind of polynomials over real tropical numbers. And then kind of the price for doing this is that certain properties that are kind of almost obvious and straightforward, for example, like summation of these integer vectors in a junction, that almost obvious if you know that it's kind of pair of pens or three circles that smoothly kind of juncted together inside of a torus. So then the fact that homology classes of this circle should add up to 0 is kind of very, very natural statement. But for them, they need to impose all these properties by hand. And that kind of makes that story more complicated in a sense that to kind of get some nice and non-contradictory intersection theory for kind of zero locuses of tropical polynomials, they need to kind of invoke some additional definitions, like we will talk about intersection theory on second half of the lecture. Like here, you see we have sort of intersection point that from perspective of radial part, here we have like a single intersection point. So in this case it's a bit not that interesting. Let me
How to see this part?
not this point. So even before that, so even ordinary intersection theory is kind of more complicated. Okay, let me kind of modify this thing. So let me kind of secretly increase the degree of this white curve by 1. Okay, let me kind of pretend that I have like more edges. So that this white curve is degree 3. So then what we know that no, sorry, I don't. Sorry, my bad. I don't even need to go to this length. So if I have a kind of degree 2 curve, complex degree 2 curve, and complex degree 1 curve inside of P2. So first of all, they always intersect. And second thing, that the intersection number, okay, P1 and C2 should equal to 2. So degree 1 and degree 2 curve should intersect over 2 points. However, in a tropical setting, here we see that the number of intersection points, it may change depending on yellow curve. Like if I choose my yellow curve let me draw it in orange. So I can choose my yellow curve to be something like this, to be orange. So here, the intersection of orange curve and the white curve, it kind of has two intersection points. So in some regions, like for some kind of coefficients on this polynomial, the number of intersection points in this kind of radial part of the curve, it jumps from 1 to 2 and back. So here is 2 and say somewhere here is say also 2.
Maybe you mean the yellow is not transferable.
No, so that apparently intersection is transversal, but kind of the idea is that previously we kind of count intersection points okay. So in real geometry, because they want to work with just a real part. So in real geometry, we count intersection points with a sign, and sign is kind of determined by orientation. And here they kind of additionally, if they forget about angular variables, they need to additionally kind of by hand introduce a new rule that we count intersection points with a multiplicity that is given by vector product of kind of vectors assigned to these edges M1 and M2. So if edges with these vectors M1 and M2 intersect, so then we additionally assign a multiplicity that is like absolute value of a vector product of two vectors. So, or in this case, it's two-dimensional vector, so it's some determinant of the matrix that is constructed writing these two vectors as columns. So that thing looks very unnatural and kind of confusing, but they needed to kind of to preserve Bézout theorem that the number of intersection points should be the same as we vary coefficients in this polynomial. So if we prescribe this additional property, then as we will see, like in examples and proof in general, then the intersection number wouldn't change as I deform this curve from this orange curve through yellow to the other orange curve. However, if we recall that here intersection is not only happens in a radial variable, but there is a torus, so then we will see that on top of this point, we have a two-dimensional torus that kind of sits on top of any point inside of this triangle. And then here, what happens, we have some orange curve that represents some homology class M2. And then we have our white curve inside of this torus that represents some other homology class. And here, so these two curves, if we look how the corresponding circles intersect over torus, we will see that the number of intersection points on torus will be precisely given by this number. So therefore, in kind of our approach of complex tropicalization, when you kind of keep track and remember that there are some phases, you don't need to kind of impose these rules. And that's the reason why I don't want to kind of include this kind of discussion of what it means to have zero locus of tropical polynomials and all this stuff, because I think this approach is less useful, at least in a context when we study like enumerative problems. That kind of the approach that I will talk, it has a generalization to arbitrary dimensions. While in tropical geometry, where originally was people kind of discovered that they can do, that the tropical counting can reproduce Gromov-Itten invariance, so this operation was kind of a key operation. And unfortunately, it doesn't generalize to higher dimensions. Because for a higher dimensional case, like you need multiple vectors. And unfortunately, like you can't construct a kind of number out of three vectors or out of two vectors in three-dimensional space. So and kind of that's the reason why I don't want to talk about tropical varieties and kind of zero locus of tropical polynomials, because I think this approach, it might be useful for something else. There are many different applications of tropical geometry, but I think it is less useful than the straight tropical complex tropicalization in approaching the problems in enumerative geometry. So that's kind of my reason why here I kind of didn't go through careful discussion of the theory of kind of taking tropical product of two tropical polynomials and then discussing what is the variety for this one. So I avoided it on purpose. Let's say it like this. So I kind of know that business, but I still think that it's not relevant for what we are going to discuss, which is using tropical geometry to describe some enumerative problems and perform mirror symmetry for this. Okay, let's still have a break. I need to have a break. So
I still want to know what happened for this. Why we can say it will be this.
Yeah, so for that particular one, I don't know, like honestly, because kind of emergence of this point means that the coefficients in defining degree 3 polynomial, that they are subject to some kind of degree 12 polynomial condition. So there is some kind of discriminant that vanishes. So I don't know like what is the kind of tropical version of this discriminant. So the only wild conjecture that I can make that this point is somehow correspond to this situation.
Yeah.
So here we kind of have a circle, but and then kind of circle shrink to a singular point. So this thing is still a kind of the remnant of some singular point in a complex geometry, because that locally looks like intersection of two varieties. So if it is true that this singular point that appears in kind of when we degenerate a curve is also locally looks like some kind of intersection point of two components. So then maybe the tropical correspondence to it would be the case when we just shrink this little square to a higher valent vertex.
Yeah, this just other confused for me. Because the geometric genus is not deformation invariant, and the arithmetic genus is deformation invariant, like this case. So I confused why we deform the tropic will preserve the geometric, not arithmetic.
So we just proven it. That
Yeah, we just proven this.
Yeah, but and here we also showed that as I perform this shrinking of this loop, I also get get like a jump in number of loops. So I'm not sure. You kind of ask it more of a philosophical question. So well, kind of I think for concrete level, I kind of showed that one operation preserves genus and that this operation it kind of decreases genus by one. So, but as I say, I am kind of maybe not that familiar with this kind of details of the complex geometry and degeneration. So that's why I can only guess that there is this kind of other potential candidate for kind of tropicalization of this situation that maybe it's some loop in kind of tropical graph of a smooth genus 1 curve, and then as we change the moduli of this graph, we eventually get to the point where this loop just shrinks to a higher valent vertex, and and that looks something singular from tropical perspective, so maybe it corresponds to singular point in kind of complex geometry perspective.
Thanks.
Yeah, so now it's 11:22, and okay, where is my break time? Sorry. 22. Okay, so today we'll make just one break to 11:30, and then we will. Okay, so next step. Okay, so we can do it. Yeah, so how about next subject would be tropical intersection series. So essentially, like when we motivated Gromov-Witten invariants, so that is secretly preparation of Gromov-Witten theory. That's essentially degree zero, Gino zero Gromov-Witten invariants. They essentially kind of expressed in terms of some intersection of cycles on our target. So therefore, first step towards Gromov-Witten theory is to kind of describe intersection of tropical curves. So we have kind of this theorem in complex geometry that tells us that if we have like two curves of degree d1, so d1 and d2, d2, so which is given by zero loci of degree d1 and degree d2 polynomials. So let's say curves in P2. Let's say start with this simple case. So then the intersection number of these two curves is exactly d1 times d2. So intersection of these two curves. So kind of the intersection. So if you look at intersection points, so intersection points are kind of solutions to this system of two polynomial equations of degree 1 and degree 2, and that kind of Bezout theorem tells us that that the number of such solutions of a complex number is precisely d1 times d2. So that's kind of how Bezout theorem enters here, and so that is Bezout theorem result. And the second result is that that in a complex geometry case, like all points kind of come with a contribution +1. So there is no this fancy orientation sign as in real geometry. So that is some kind of theorem or extension of Bezout theorem into algebraic geometry over C. So now the question is like, what is a tropical version of this thing? So we already know how to draw a tropical curve in P2. So tropical curves are essentially graphs drawn in P2 with some rules. So okay, so for now, our working definition of degree D tropical curves is that we start with kind of reducible degree D tropical curve, and then deform these higher valent vertices into 3-valent vertices, and what we got some kind of graph. So let me look at kind of describe our basic example of degree 2 tropical curve. So it's kind of degree 2 tropical curve. And then we take kind of orange thing and yellow and draw a C1, which is degree 1 tropical curve. And let me draw another degree 1 tropical curve, let's say like this. So all these like tropical curves of different color, like yellow and orange tropical curve, both of them are degree 1 tropical curves. And then, therefore, according to kind of this theorem, which is extension of Bezout theorem in algebraic geometry, so the intersection of C2 with C should be the same as the intersection of C2 with this orange C, and should include curve. However, observing from this explicit picture, we see that there is a kind of topological difference between these two situations. So in one case, on this kind of space of real values, or in this toric polytope, we have one intersection point. So one intersection point for yellow curve, but two intersection points for orange curve. And in general, okay, so in this setting, if we kind of vary our degree 1 curve, I think like avoiding the situations when we have like coinciding edges. So there is like a special situation when, say, this orange edge would coincide with one of the white edges. So that situation is non-transversal. Okay, so I think you asked the question. So let me draw it in yet one more different color. Let me use temporary green. So that would be non-transverse situation. So let me just draw it. So this green curve C intersects C2 non-transversal. So here it's not like some multiple intersection points, but a situation when one of the edges, when kind of pair of edges from blue curve and from green curve and from white curve, they coincide. So that is kind of tropical version of non-transversal intersection.
You mean if we intersect with a multiple point?
Yeah, so here, like you see, it's not even isolated points. It's just kind of the whole semi-infinite edge.
Right.
Yeah. So here we don't have. Yeah, dimension is wrong, because generally intersecting two kind of curves in P2 should give us some finite number of points for transversal intersection, because we have like two objects of dimension 1 intersecting inside two-dimensional objects, so transverse intersection tells us that they should intersect over a finite set of points. While in non-transversal case, you may have like some components of this curves coincide, and the tropical version by coinciding components means that like pieces of edges of these two curves coincide.
But in geometry, even we intersect to a dual point, we not call this transverse.
Okay. So in geometry, I agree that it's necessary but not sufficient condition. Yeah. Okay.
So what happens with the
Okay. So that is also an example of non-transverse intersection when it's clearly non-transverse.
we will call this case not proper intersection in some.
Okay. So if there is some kind of additional classification for
Bezout's theorem.
But this intersect at two isolated points. Why don't we call it transverse? Because at each local neighborhood of this intersection point, it's only
Transversal means the tangent vector.
yes.
Yeah, but
at each point is the tangent.
you see. Okay, let me kind of classification. So that is
picture is
kind of non-transverse intersection. So let me draw parabola and a line. So you can imagine parabola intersecting this line at kind of lowest point of this parabola. So that is non-transverse, and that would be transverse intersection. But in kind of in a tropical setting, So here kind of non-transverse intersection in a limiting case goes to kind of tangential intersection. So these two curves, they kind of share the same kind of tangent space.
Yeah,
So in the tropical curves, like the analog of this tangential intersection is precisely this green situation. So that is at least the part that I know. I'm not sure that every non-transverse intersection. No, I think by construction every non-transverse intersection is a tangential intersection of some kind, because the tangent spaces to two objects should have a common kind of subspace inside of a tangent space at a point. So it means that there is some kind of tangency condition.
Yeah, I mean a more formal Basel theorem in algebraic geometry. We can contain every proper intersection by the length of the intersection subscheme.
Okay, that is kind of some generalization that I'm not familiar with.
Okay.
Sorry, so that's why the thing that I know that in this case, like, so this intersection of like green degree 1 curve and this white curve is a tropical analog of this situation.
And the yellow one is the right hand side. The yellow intersection, even though it's
Yes.
But what's the difference? The yellow and the orange.
Yeah, so in algebraic geometry there shouldn't be any difference between yellow and orange. So both yellow and orange they are kind of in a general position. So green one is not in a general position, because for green one, if I slightly move this vertex, so then I can avoid this tangency. So while for white case and orange case, if I slightly move white curve and orange curve, I still have the same topological situation, that the number of points doesn't jump if I vary position of this yellow vertex or orange vertex. So and this kind of raises a question. So because from algebraic geometry perspective, there shouldn't be any difference between yellow and orange case. While in tropical geometry, naively, there is a difference. However, there are kind of two ways of resolving it. So one way is, as I mentioned, this kind of traditional tropical geometry. So traditional means like thinking of tropical geometry as an algebraic geometry over tropical numbers. So in this case, people say that we need to introduce additional definition for additional axioms that tells us that kind of for each intersection point on this kind of polytope, or for each intersection point between kind of two tropical curves, then what we need to do, so each intersection point is kind of intersection of two edges, like E and E. Like locally, it's intersection of two edges, and we need to introduce multiplicity z equal to kind of, okay, they I think have a formula like this. So we take like this pair of two-dimensional vertices for E and T prime, we form 2 by 2 matrix and compute its determinant and take absolute weight of this determinant. So and then kind of proposition that given this additional weight, so for okay, and kind of the definition for intersection of two tropical curves will be sum over this intersection points of the corresponding graphs, and here we will like weight the contribution from each point with this factor, and that would be our tropical intersection number. let me put subscript T. So, and then kind of proposition is that the tropical intersection number is invariant under small deformation or under deformation. So that's kind of how people approach it usually, and let us prove this proposition. So let us see, let us kind of describe a local situation when the number of intersection points change. So once again, here we are working with smooth tropical curves or smooth tropical curves. So I think like for now we will prove it for smooth tropical curves, but I think the proof can be further extended for non-smooth. So let me prove it for a smooth, or let me kind of prove for smooth case. Okay, so in a smooth situation, kind of a jump in the number of intersection points happens when an edge of one curve kind of passes through vertex of other curve. So the jump in the number of intersection points happens when the edge of one curve crosses the vertex of other curve when we deform. So we can imagine that is our deformation. So we deform our, say, kind of one of the curves. We deform it in such a way that the red edge goes to a yellow edge. So that is our kind of deformation, and we can see that locally, kind of every jump in a number of points is related to this situation. That under the deformation at some point we cross the vertex of other curve. So therefore, and because our total intersection number is kind of sum over these points, so it is sufficient to investigate kind of whether there is a problem in this local jump, in this local situation. So if there is no problem for every local situation, then there is no global problem, because kind of globally the intersection profile kind of is a combination of local profiles. So in the kind of general setting, we can assume that we always intersect vertices one by one. So as we deform curve, there is never a situation that we simultaneously intersect like two vertices when we deform. So we assume that we are in generic situation that we intersect vertices, that we intersect one vertex at a time. As we deform. So we intersect one vertex at a time, and for single vertex intersection, we have these two pictures. So on one kind of value of a moduli, we have two intersection points when we intersect like these two incoming edges. And then after the deformation, we have a single intersection point when we intersect outward edge. So once again, let us kind of use our definition with multiplicities. So let us look at kind of change in intersection number. So the change in intersection number under this local deformation would be what? So it is intersection number which is yellow, which will be contribution. Let me give us some names. Let me give an M1, M2, and M3. And for this other edge, let me just call it M. So M is a tangent vector to this yellow and red edge. So what we have? So at the final point, we have like M times M3. Okay. Determinant of these two vectors absolute value. And what we need to subtract okay, now, sorry, yes, I think I don't really want absolute value here. So that will leave me with a question why the intersection number is always positive. But let me kind of avoid this question and kind of refer you to a proper literature. So and then kind of so that is orange situation, and then kind of red situation would be determinant M, comma M1. Determinant M, comma M2. So that is my red situation, and then I recall this vertex balancing condition. That if I have orientations like it is here, that M1 plus M2 is M3. So then if I have kind of sum of the two determinants, so this determinant can be written in following way. This is M, and here I take a sum of these two vectors, write it in a second column, and take the determinant. And then kind of vertex balancing condition basically tells me that it is determinant of M3. And that is the same as we had after the number of intersection points drops by 1.
So what does mean for this determinant?
So we have like two-dimensional vectors.
Yeah.
You just write these two-dimensional vectors as the columns.
Yeah.
And you have 2 by 2 matrix, and you compute the determinant.
Why this is linear as the
Linear and
second term? Why we can plus M1 and M2?
Because determinant is okay. So let me rewrite it in a different way. So this okay. So suppose I have like determinant of M and N. So let me write it in several different ways. So let me write it in components. So that will be like M1 and 2 minus M2 and 1. But this thing you can also recognize as a vector product of two vectors, M and N. So and then if we kind of recognize that determinant is a vector product, so then we have like M vector product with M1 plus M vector product with M2. And vector product is kind of linear in both arguments. So therefore, if you have vector product of a same vector with M1 and once again the same vector with M2, so then by linearity of vector products, this thing is M Or you can just say here that determinant is kind of bilinear in components of these vectors. So that's why we can kind of, if we have sum of two determinants, then it is the same as determinant of between like fixed vector and sum of two vectors.
If we need this M to be a normal vector, to be a
No, M is kind of arbitrary vector. So,
okay, so epsilon p can be arbitrary.
yeah. So this thing can be arbitrary. So that kind of leaves a tiny question why this thing is positive. But that is something that okay I want to avoid for my discussion, because like what I want to say that is this kind of traditional approach. So in traditional approach, you recognize that there is an issue, because in traditional approach you only have this two-dimensional story, so you don't have any torus sitting on it. So that's why in traditional approach, best you can do is kind of by hands assign some additional weights to these intersection points, and then kind of verify that your assignment of weights kind of combine it with some other nice property like vertex balance condition, kind of gives you invariance of the intersection number. So that's what kind of these people like Mikhalkin, Gross, Markvik, and other kind of people doing tropical geometry do. So they say, yes, there is a problem, but there is kind of a nice solution to this problem, and they kind of treat this nice solution to a problem as an additional justification why we should have like this vertex balance condition, because it ensures that the Bezout theorem kind of holds for intersection of tropical case. Okay, so that was kind of one approach, and kind of our approach is the following. So our approach is complex fertilization. Complex fertilization approach. So in complex fertilization approach, so when we have an intersection point, so we have this intersection point here. So we know that that here all this picture is essentially only half of our complex manifold. That on top of this red point, we have two-dimensional torus, and therefore kind of here intersecting over red point, it's only intersection in half of the dimension. So to basically see a kind of points of intersection, we need to study what happens to this kind of orange, to this yellow and white curves in this red two-dimensional torus. So let me draw this red two-dimensional torus as kind of a square or rectangle with sides identified. So that would be easier to kind of see the intersection. And then what you have, we have a picture like this. So we have some white curve in this torus. So that is my white curve. So white curve kind of has some, I don't know, winding number. Let's kind of actually compute what are the integer vectors in this case, because we expect answer to be 2. So for orange curve, it's very easy. So the integer vector is just 1, 1. So the orange curve kind of oriented like this. So it kind of so this edge is actually semi-infinite edge. So semi-infinite edge crossing this compactifying hyperplane. So it should have a vector which is equal to a normal vector of this compactifying hyperplane. So this M is 1, 1, and 1, 1 in the case of a torus So that is something like this. So that is on a rectangular torus. So that is vector 1. Okay, let me draw. On a torus, so that is kind of 1, 1 on this torus. So it just kind of winds once over each side. So now let us calculate this vector. Okay, let's call it m prime. So m prime, which is integer vector assigned to this white edge. So that is a bit more complicated calculation because like we can't just guess the slope because I'm bad at drawing. So therefore we need to compute the slope. So how we would compute the slope? So let us notice that to get to this edge of a question, it kind of obtained. So we can get to this edge by kind of looking at a sort of upper part of this curve. So upper part of this curve consists of 3 semi-infinite edges. So we know that for this edge, the tangent vector 1, 1. So for this edge it's horizontal 1, 0, 1, 0. So let us give these orientations. Okay, so here 1, 0 meets. Okay, so if we do orientation like this, then it should be -1, -1. So here 1, 0 meets -1, -1. So that gives for this vertical edge -1, sorry, 0, -1 if it is outgoing. So if it is outgoing, then its vector is just the sum of these two incoming vectors. So now here we have 0, -1 and 1, 0 as two incoming vectors. So therefore here if you assign orientation outgoing, so then this vector would be a sum. So this vector would be 1, 1, -1. Okay, so that works. So let us first do an old way of this determinant formula. So this vector is 1, -1. That is our m prime, and for vector m is 1, 1. Okay, so up to a sign. So the determinant gives us 2. It's this. So now what about kind of torus picture? So on a torus, we have this another. So we have like one kind of cycle with a winding number 1, 1, and another cycle with a winding number -1, 1. So I think this cycle it will look something like this. Okay, let's do it in orange. So and therefore on this red torus, the intersection points for these cycles is okay, let me see. So it's okay. So the one that I draw, okay, 1, 1, -1. So it's still kind of. So it still kind of grows in x direction, but falls in y direction. So 1, 1, it kind of grows in both x and y direction. So while the other cycle, which is 1, -1, so it kind of grows in x direction, but falls in y direction, and we kind of recall that this picture is periodic. So when we reach 0 here, it's the same as the starting. So what we see that on this torus. So on this red torus, these two kind of circles that are fibered on top of orange and white lines, they actually intersect over 2 points. And therefore, in our approach, yes, we can count these 2 points by computing determinant, but we don't need to give any new axioms. We just need to carefully analyze what is the intersection of circles fibered over that point. So that's kind of why I like our approach better, because it doesn't require additional axioms. It just requires additional analysis of what happens in kind of fibered dots. Okay. This thing. So okay. So in this intersection theory, intersection theory allows us, like recall when we talked about more general Gromov-Witten theory. So Gromov-Witten invariant was kind of depended on a degree, and degree was in general some kind of class of the curve in some kind of positive part of second homologies of X. So that essentially means that degree is roughly a collection of, okay, so let me look for a second Betti number of X, B2, okay, positive integers. Okay, okay, so here it's not clear whether they're positive or B2 integer numbers. So that's kind of what we had in Gromov-Witten theory. So let us try to understand how to see this kind of rough description of a degree, like if we omit this positivity part, that the degree is always positive. So if we just look at how many integer numbers we need to provide to specify the class of our curve in H2. So usually we need to specify like as many numbers as the dimension of H2.
Excuse me. Even though we know all the slopes, the intersection number in this square can be just one. For example, the orange line is they are all diagonal. I mean, you can imagine there's a cross in this square. Does it depend on the position you place these two lines?
Okay, I'm not sure. It feels like the cross would be some kind of special position.
Yes, you are right. But I mean, you can also find some, because the cross, both of the lines will go through the vertex. The vertex is another intersect.
Yeah. Okay.
But
okay.
I think you can still draw something that they intersect at one point.
No, I think that's not possible.
So you should assume this red square to be like equal lengths, like a square, a regular square, right?
Yeah, but that's kind of what says. So here, let's see. Yeah, I think here we assume that it is kind of square torus. But I think the final result should still be kind of equivalent to this computation of just computing determinant of this pair of vertices.
Yes, I'm convinced. Yes, it always intersects at 2 points.
Yeah. Okay.
Yeah, if you are given this perpendicular slope, then it always happen intersect at 2 points. But yeah, just like in the second case, if you have some other slopes.
Yeah. So then it will be generally one point. So I think in this situation, like for example, for this point, the picture would be like this: that there will be something like vertical line and horizontal line, and that would be just single intersection point regardless of.
But in the higher degree case, is it possible to have some other slopes other than this 1 + 1 1 minus 1.
Yeah. So you have like pair of integer vectors. So here you can imagine like adding more and more these external edges. So that's kind of where we are going right now. So kind of generic vertical curve is some kind of graph drawn inside polygon. And kind of we will give a full definition next time, but among the properties that we will require next time, so there are two properties that we already saw, that external edges so they are kind of semi-infinite edges. So that's how they call semi-infinite edges. That what people in tropical geometry usually call them. I kind of prefer physics notation, external edges. So semi-infinite edges have this E belong to this space of compactifying of space of normal vectors or compactifying divisors. So that is the set of all these vectors B that define kind of compactification of this polyton, compactification of Rn to our polyton. So then integer vectors on edges meeting at the common vertex satisfy balancing conditions. So it essentially means that with some proper orientation that we'll discuss next time, that they add up to zero. That the three vectors after we choose orientation, so it's kind of plus for incoming orientation, minus for outgoing orientation. So if all three vectors are incoming, then this is just sum to 1 to 0, and if one is outgoing, then it means that two other sum to the third one. So that are two properties among kind of full list of properties. But just judging on these two properties, we will see that that kind of homotopy type of the curve is essentially defined by specifying like B2 of x integer numbers. Okay, so how do we see this? Let me okay, so we have our kind of polyton. Let me do something more general, and that we have some kind of graph drawn inside of a polyton. Okay. Okay, so I kind of draw a rough picture. So the sum of the vectors may not quite add up to 0, but roughly this picture. Let me draw edges with different colors. Okay, so and we can have I don't know, some picture like this. So then what we can do the following thing. So we know that that each external edge so for each external edge that process HP so it should have M equal to this B. So therefore here for this hyperplane we have some vector B, B1 normal vector. So it means that these two edges that they are ME and ME prime, so both of these vectors equal to B1 if we orient these edges kind of inward. So let us, so that is the first property. So that is kind of specification of this property. Let's give one here, 3 and half. So that is kind of specialization of property 1. So we explicitly say that that if edge crosses particular hyperplane, then the tangent vector to this edge should be equal to normal vector. So then to kind of use property 2, we take another specialization. We orient all external edges to be incoming. So all internal edges are oriented from infinity to kind of finite part of the graph. So all these external edges are oriented like this. So now we use property 2 again. We use it in the following sense. So we know that for every vertex, the kind of sum over incoming vectors would be equal to sum over outgoing. So that is also kind of careful specification of this science. So now this rule it kind of holds for kind of subgraphs as well. So if I have something like this, so then I first apply this rule. So say M1 and 2 to get M3, which is M1 plus M2. And then I have like M4 and M5, which are also incoming. And then balance condition at the second vertex will tell me the following thing. So now M4, M5, and M3 are all incoming. So from this we will get M1 plus M2 plus M3 plus M4. Sorry, plus M3 is 0, and then using M3 through M1 and M2, M4 and 5, we will get M1 plus M2 plus M4 plus M5 add up to 0. So therefore, like this linear property of kind of vertex balance condition, it kind of can be extended globally. So if I have globally some kind of graph and I know integer vectors assigned to all of its external edges, so then the sum over ME, where E belongs to external edge, and all of them oriented inwards, should be equal to 0. So that is just can be proven by induction, by going kind of vertex by vertex. That here, like taking into account these two conditions, or you can say that this vertex balance condition is kind of preserved under deformation. So I can deform this smooth tropical curve into a singular tropical curve by just shrinking this internal edge. So that's why here I can also shrink like all these internal edges and internal loops. I can shrink all the business to a single vertex, and instead of this complicated tropical curve, I would just get a star. And by shrinking, I still kind of preserve this property that I preserve balancing conditions. That for every new vertex that I got, I still got this property that sum of the incoming vectors equal to sum of outgoing vectors. And if all vectors are incoming, then they should add up to 0.
Yeah, but there is a loop inside.
Yeah, but when I shrink the loop, so that is kind of non-obvious, but you can show that shrinking the loop also preserves this property. That if you have vertex balance condition at each of the vertices of the loop, then you can show that presence of the loop gives you like some kind of one independent vector that runs through the loop, and then by shrinking the loop you just kind of remove this independent. So it's like these 3 vectors that satisfy balancing condition plus 1 freedom vector that can run in the loop. And kind of shrinking the loop means that you just forget about this extra vector. So that is like for people familiar with physics. So these properties, they are like momentum conservation. So when you have some kind of scattering diagrams for particles in kind of Lorentz invariant quantum field theory, then your kind of scattering preserves the momentum because of the Lorentz invariance, and therefore regardless whether you have some loops or something, so you still have, like, if all particles oriented incoming, you still have some of the momenta equal to 0. Or equivalently, you can say that if I orient all momenta to be outgoing, it means that you kind of particle at rest just decay it in multiple of particles, so in kind of multiple particles, and initial momentum for particle at rest was 0, and that means that the sum of the momenta for all outgoing particles is also 0. So here it's kind of like analog of momentum conservation. Okay, so now I need to kind of specify what it means to specify homotopy type of curve. So to specify homotopy type, for curve, we specify the collection of integer numbers collection of natural numbers D. I don't remember whether I call them A. So A is kind of like a label for this vector B. So dA natural numbers 1 for each compactifying hyperplane. So specifying homotopy type of the curve is kind of specifying behavior of our curve at infinity. And behavior at infinity is essentially specified on kind of how many infinite edges of a given type we have. So dA kind of this kind of number of edges of external edges with tangent vectors equal to VA. So we have a collection of compactified hyperplanes specified by this integer normal vectors, and any tropical curve it should have external edges aligned with this normal vectors. So therefore, to specify homotopy type, we need to specify how many these external or semi-infinite edges of a given type we have. So that will give us a kind of collection of numbers gain. However, vertex balance condition, okay, and here kind of subsets to vertex balancing. Because we see that we can't kind of assign these numbers independently, because if we have, say, only infinite edges of one type, so then there is no chance we will satisfy vertex balancing condition, because we will just have like some number d of edges whose tangent vector equals to say d1, and the total sum of such edges would be like d times b1. That will be contribution from these edges, and d times b1 is non-zero, is only zero when d is zero. So the only way to kind of satisfy vertex balance condition is to say that we don't have any kind of edges that go in direction of b1. If we only have one type of edge. So if you have multiple type of edges, then there are multiple ways of satisfying vertex balance condition for different choices of D. So therefore there is kind of natural question. So how many choices of DA we have? And 20 choices means subject to this balancing condition. So that was just. So therefore, balancing condition gives us some system of linear equations. So sum over ME, where E belongs to external edges. Okay, let me just call it E of gamma should be 0. And if we assign this dA for external edges of a type A, so that this sum will be sum over n from 1 to this capital B. So capital B is just a number of this compactifying divisors. So this one should be 0. So we have B kind of variables which are dA. So we specify the number of edges of a given type. And then here, because it is a vector equation, so vectors B itself, they kind of vectors in some n-dimensional Euclidean space. So they integer valued vectors. Okay, let's say that they are integer valued vectors in n-dimensional space, where n is kind of complex dimension of x.
No, E gamma means all edges or all external edge.
Okay, let me. I kind of X also bad because it's also reserved notation. So okay, let me temporarily call it external edges, or let me call it EE. External edges. I think now it's better. So okay, so we have B variables and dim C of X equations. So given that this matrix B1 So we can arrange these vectors into something like V by N matrix. So given that this matrix is maximal rank, so then the kind of the space of solutions is has dimension. So space of solutions is a vector space. So if you have a solution, then the linear combination of solutions is also a solution. So the space of solution is a vector space whose dimension is what? So it's number of variables, capital B, minus number of equations. So now let us recall that B is a complex dimension of X. Sorry, this N is a complex dimension of X. So we get this formula that is kind of number of compactifying divisors minus complex dimension of X. And I think few lectures ago, maybe 2 or even 3 lectures ago, when we discussed toric varieties, we explicitly showed that this thing is the same as the second Betti number of X. So when we used this, I think Fulton's method of kind of computing the Poincare polynomial for a toric variety by counting kind of orbits, counting contributions of orbits of different dimensions, one of the corollaries was that the number of compactifying divisors minus dimension of X was precisely dimension of second homologicals. So here I kind of in my logical steps. So I started with these DAs, which have natural interpretation of positive numbers. So here, but here, kind of when I went to space of solutions, it was space of solutions over Z. So I think kind of to get a full proof, I need to perform one extra step to show that the number of solutions with a certain positivity property has the same dimension. That among these solutions with possibly negative coefficients, there are like the same dimensional space number of solutions whose kind of vectors belong to some positive form. So, but modulo this small issue, we see that essentially the number of kind of integer numbers defined in a degree of a tropical curve is essentially expected number that we saw in kind of complex geometry. That if we define our homotopy type of a tropical curve by just specifying behavior of our graph at infinity, by just specifying like how many of a given type of semi-infinite edges we have, then vertex balancing condition would reduce this number exactly to kind of expected dimension of homotopy type of curve. So that was kind of verification that the definition for kind of tropical homotopy type eventually matches the definition of homotopy type in kind of complex geometry. And
when we call this homotopy type, if we shrink a loop, it will change the homotopy type of the graph.
No, for a graph, yes, but to say. Okay, maybe this word is the wrong word. Let's kind of call it tropical degree.
Oh, that means a curve class.
Yeah, tropical curve class. Yeah, I think that.
Okay.
Yeah, tropical curve class. So, yeah, I wasn't like very explicit because there are different topological characteristics. So one is kind of internal topology that changes as we shrink, but kind of curve class it doesn't change if we change genus. So like we had the degree 3 curve that can be genus 1, and if we kind of deform it to a singular curve, it is genus 0, but still degree 3 curve. And kind of tropical curve class define it as specifying number of semi-infinite edges of a given type, kind of matches with ordinary curve class in a complex geometry, and that is generalization of a degree. Like in P2 case, the dimension, the second Betti number for P2, or generally Pn, is 1. So therefore the curve kind of class is defined by single positive integer number. And we can verify, so let's say example. So in P2 case, so let us explicitly write these equations. So we have d1, d2, d3, these numbers, and for our vectors, vector b, so b1 was 1, 0, b2 was 0, 1, and b3 was this kind of -1, -1. So therefore, these equations would essentially say that d1 minus d3 is 0, and d2 minus d3 is 0. So here we see that kind of coefficients of this equation essentially say that d1 equals to d2 equals to d3. So in this case, indeed, there is one-dimensional space of positive degree solutions.
Maybe it's better to say B3 is 1, 1 in order to make D1 equals to D3.
No. If it's 1, 1, then it will be d1 plus d3. No. So here we want them to orient inward pointing, because
the assumption is dA times BA.
Yes.
They sum to 0.
Yes.
Here.
d1 times b1. So that will give, like the sum will give me a vector with components like d1 minus d3 and d2 minus d3. That will be my two-dimensional vector, and vanishing of this vector implies that these three integer numbers should be the same. And a similar property immediately holds for Pn, because Pn is some natural generalization of the structure when we have like just n coordinate vectors and one vector with all minus ones. So if we add them, that will immediately give us conditions that all these keys should be the same. So that kind of construction gives us another way of engineering kind of curves. Of engineering tropical curves in P2, like previous way of engineering tropical curves was to start with kind of a tropical curve that is reducible, and then kind of deform it to get multiple tropical. So an equivalent way would be to say that, let's say, we want to construct degree 2 tropical curve. So by this construction, degree 2 tropical curve means that we have kind of exactly 2 semi-infinite edges of each type. And then what we need to do, we need to somehow join these edges into graph by preserving vertex balance condition. So one way would be doing like this. So vertex balance condition would say that this thing should go vertical. So here, what we can do? So we can, maybe we can join these two. So then it should go like this. Okay, with this incoming and and then maybe join like this. So that kind of gives us another perspective on drawing tropical curves, is that you kind of start with the semi-infinite edges and somehow join it into graphs. However, you need to be careful that the vertex balance condition is kind of quite restrictive. I think I will put this into homework exercise, but maybe I can just without the homework exercise would be to prove it, but just as illustration. So kind of if I use this procedure of constructing tropical curve, I can imagine the following situation. Let me look at degree 2 tropical curve. So I have like semi-infinite edges, like two semi-infinite edges of given types. So let me kind of join them pairwise. So I will get something like this. And then I can imagine the following situation, that I kind of suspend a triangle using these three edges. And naively, this thing gives me degree 2 genus 1 tropical curve. And as we discussed by kind of other method of constructing tropical curve by deforming reducible tropical curves. So that should not be possible. So for you, homework exercise would be to see that that kind of given these three vectors, that each of them is the sum of two normal vectors to boundary divisors, that there is no way to satisfy a vertex balance condition for each of three vertices for this triangle. So this picture is prohibited or ruled out, is ruled out by vertex balance. So that is kind of nice exercise. And that was the reason why kind of in my construction I started with reducible curve and deforming it, because in that way we can't run into issues. But then after we learned kind of a better way, which is so this way of starting with reducible curve and resolving it is kind of very hard to generalize to higher dimensional case, because for higher dimensional case generally a pair of curves, they do not intersect because of kind of lack in the dimension. So it's a curve and hyperplane intersect of a point, but pair of curves do not intersect. So that's why it is kind of hard to construct higher degree curves by resolving intersecting degree 1 curves, because generally they don't intersect. While this method of starting with edges with a given tangent vectors and then kind of attaching some internal edges to this external edges and turning this picture into graph is a construction that works for arbitrary dimension, and that is a construction that we will use to kind of enumerate the tropical curves with a given properties, like passing through some cycles. But what you need to check is that this property indeed kind of constraining enough to avoid these cases that looks correct, like here. Okay, so in this picture maybe there are like some integer vectors assigned to these edges such that vertex balance condition holds, but apparently there should be none. Okay, I think I'm already went over time, so unfortunately I haven't reached like moduli space dimension counting, but I think it's good, so we still have enough time in this course to catch up. I think next Tuesday is a holiday, so next Tuesday is May 5th. But I was told that the Tuesday, May 5th will be compensated on Saturday, May 9th. So therefore, our next class will be Saturday, May 9th. That is kind of compensation for a Tuesday, May 5th. And then we will kind of efficiently have like almost like 2 classes in a span of 3 days, 4 days.
May 19th.
Yeah, it's the same time. So I think like at least what I was told that officially like Saturday, May 9th, like scheduler wise works like a Tuesday. So the courses that are scheduled on Tuesday, May 5th would happen at the same time at the same place, but on Saturday, May 9th. So that's why I'm just stressing this out. But most of you probably familiar with this kind of compensation business because in Western countries they usually don't do this long holidays with compensations. That's why at least I was. It took me some time to get used to this idea and kind of start specifically asking secretaries like what is the compensation day for this working day on the weekend. Okay. So I will. I'm a bit behind in homeworks, but I think in the worst case scenario we will just have. I think I promised to have 7 homeworks, but maybe there will be like less, maybe 6 or even 5 homeworks. For previous material was not kind of covering enough topics for me to make like interesting problems that are useful in the later part of the course. But now, kind of after we discussed tropical Bezout theorem and tropical intersection, so now I have enough materials to make some nice questions about tropical geometry. So I will kind of compile the next homework in 1 or 2 days. With some. Yeah, probably due day would be Saturday, May 9th, so that you still have time after holidays to work on it. So I will compile it in 1 or 2 days, and you will have like slightly more than a week to work on. Okay, so thank you.
Oh, I
Yes.
still have a question.
Okay.
Now we talk about the degree of a tropical curve class.
Yes.
In Grunwald-Witten, the degree means a degree of a stable map. I think it's a different. One is a degree of a subcurve in P2. Another is degree of map.
No, I think in case of P2, degree of map and degree of curve are the same thing. So.
You mean the degree of the image of this map?
Yeah, so I think so degree of map is the same as this kind of curve class understood as a degree of the curve class of image. Yes, so I think that I think is kind of correct statement. So I agree that usually, like especially when we talk about rational curves, we can describe these rational maps, say in some parameterized form. That we start with some local coordinates z0 and z1 on P1, and then we say that the map to say P2 is a collection of 3 degree 2 polynomials in 2 variables, like modular overall kind of multiplication by complex number. So that would be what people call quantity maps, and kind of maps are some subset inside of quantity maps. And in this case, the degree is kind of very natural, is the degree of these 3 polynomials in parameterized form. But if you look at kind of a curve given by these 3 polynomials in parameterized form, like formally we can kind of write down a single degree D equation that will be like curve as a variety. So the degree of this equation will be precisely equal to degree of each of these 3 polynomials that define the curve in parameterized form. So therefore, at least for P2 or Pn case, the definition of 2 degrees they match. And I'm not sure how to define degree of the map for say higher genus map. So for genus 0, yes, I can kind of extend this procedure at least to other toric varieties, like this parameterized form of the map. But for higher genus, I'm not sure what is the natural definition of degree of the map. So,
Yeah, my confuse is we not consider the domain curve. In Gromov-Witten, we can deform a genus 1 map to a nodal curve,
yes.
right? But a nodal curve is also a image of a P1. So it's not only in genus 0 case, it's still considered in genus 1 case.
Okay. Maybe you can, but I usually was always thinking of degree as this kind of curved class, but I agree that strictly speaking, you can give two definitions. The degree of a map that I think is defined as some kind of taking a pullback of image of your curve and integrating it over curve that will give you some integer number, which is kind of like roughly counting number of images for a single point. Yeah, that would be degree of the map, and but I think I'm not sure what is the proper reference for theorem, but it feels like that this thing should coincide with this curve class definition of degree. But I don't have a proof on top of my head, so I will kind of think about it, and if I get some nice proof, I will tell you next time. Okay.
这真好吃啊！
我算了一下啊，自从光一个感觉需要你看 degree one 的，
对，
还是底下有 degree one，
对，你看这个限制太强，
感觉这个
这个感觉不太行。
为什么不太行？就是你
你随便画画，但 degree one 里面它的每一个 edge，它的 slope 都是固定的，都是要么就只能10011这种东西，是吧？它长不出其他样子来。
哦，对，
因为它每个如果你要输入就只有一个，但是如果你有 degree two 的话，可以输入2个进去以后，它会变成2 slope 2这种 slope 也有。对，你比如 degree one 的时候，它是，你怎么看 degree one 是怎么一回事？
我觉得这个限制还是只有一个。
对，感觉 slope 的限制很强，是吧？
但是 degree two 里面哪有 slope 2也没有。
有的 slope 2的可以有，然后你这两个现在又是一个2的。这样子就是一个，
它不能被摁着在
问题在这个上面，所以就需要再继续啊，这里面这个2的，你得拼一个这个上去，拼一个
应该是零负一的
，0负1的，还有可以变成一个正常的1。
零负2应该是
对啊。这样， 对，这，
那我觉得就是在2.0 local 上有个限制的，可能不能超过2。它那个像美对不对？
对，但你这样随便限制一下，它是完全是可以有这种模式，对吧？就是有个2的，有个2的，然后其他都是正常的1负1的这种，可以画出一个这种。
我也肯定是画了一个，感觉是有点，是不会。
对，它肯定还有什么有2的那种边的，那种边的个数也不能太多了，好像。
对，应该只会有一个。
肯定跟它那个边数 external edge 边数有关系。
到300分。
哎，话说，哎，上次看那个录像还能，
它没有自动录，
哦，
它平时都是自动录的，上次没有自动录，所以这个昨天跑过来一看，发现没有，问 IT 说也没有远程录，所以有点遗憾了 ，sorry。对你可以有，比如你上次有什么？上次我笔记发
哦，看我看，对对
但是可能比如computing那个都字比较难看了。
不是你有没有什么 comment？
就是反正就他上次先讲了个 tropical rain， 反正tropical rain， 反正就是加法乘法讲了一下是什么东西。
这个我看。
对，就把那个一次的曲线变成一个三，就是这种 three valent 的一种图，就一次的一根曲线变成 three valent 图。然后但这种图它画的都是它的 real part， 就只画了它的那个 radius 那种，就是你把它的就这种其实它的那个 target， 就是它 target 是一个2维的那个 complex variety 之类的，是它跟 target variety， 就它的 target 是个2维的，负2维的，但是它只把它两个实物画出来。
我大概明白了，就是他之前讲 toric variety 的时候不是说这个图这样，它上面每个点都有一个题库，
对，
相当于它底空间是2维12维，它的 fiber 也是12维。
对，这个三角形上面是 C， 它是把 C2 的那个两个实物画的这个三角形。OK， 就把它跟 R2 那个截。
然后我感觉它这个 intersection 有点像是我在一个4维空间里让两个12维东西做交。那么你投影到底下来，如果有一个焦点，你底下也有焦点，然后它上面的那个 case 我感觉像是它的 fiber 上有2个焦点，
对，
所以一共有2个焦点。
它这种这个
对，
这个在它是只画了它那个实的，在R2上面的焦，就是
我觉得更像是对，我觉得更像是把它投影下来，
对，
还是扔到这里。
它还有2个 S1， 还有这个方向上的画出来。
对，
这个，所以它前面画的就是那个在那个地图上面去画那个2个焦点，有可能是2个点。对。
然后这些 M1 到 M 是可以随便取的嘛？对，就是只要满足它那个 balance 条件。
对，它就外面这个不是随便取，就是这些都是固定的。
但是这个东西我觉得也是，就是当然它是有限条件，但我的意思就是你这个靶向量你取2的，
如果你是 x 固定的时候 ，x 这个 toric variety 固定的时候，这组 data 是固定的。
但是这个你可以乘倍数，你可以把这个东西扩大缩小。
对，这个可以乘倍数，但它有一个条件是，就是首先这些比它放在一起，它是一个什么就是它互反正就是互素的那种。如果你有素因子的，你要把它除掉的。
OK， 就是相当于
这叫 primitive，
极小的一个。
对，有点像是 primitive 的。
但是我觉得我们这套构造，你成比例的是没有影响的吧？如果你把所有的 vector 都扩大1倍，你把这里所有的 r
所有都扩大，但我的意思，如果你单纯扩大一个的话，
这个你就直接变掉了，这个就
这个有点问题，所以它一开始约定的时候都是 primitive， 就是这些 compactification vector， 就是它这些 vector 是来自于这个 toric variety 的，是 compactify 一些 divisor， 那些它在就是这些都是它的
我有点好像明白你刚才说的这个条件，就是这个 case 为啥不行？就这3个向量，你说把第一个只扩大2倍，剩下不扩大为啥不行？
对，它这个是，
但是它不满足手，
它
守恒率就是这3个加起来要等于1倍。 这个是确实的，这个是不 balance 的一个 case。
对，
但是我 confuse 的地方是，
哎，对对，你换成 balance 的，它
我只要换成 balance，就我的意思是，
换成 balance 也行，换成 balance 你比如说这个就换成负2，这个也行，它可能换出来的
这个不行，你必须要是负1的倍数，因为你要是这个的 normal value。
它可以把那个，我估计它是可以换成这个样子，就是它那个 toric variety 那个 polytopes 可以画成一个另外样子的三角形。它因为它这个三角形画的三个 normal
就是不等腰的三角形。
对对，不等腰的直角三角形，可以画成这个样子。我感觉，对，它就是相当于这些东西，它这些数对应的都是类似于一个 holomorphic mapping， 它把比如这个负2、负1什么的，它大概长这个样子，负2次方、1次方的样子，就是这些2、1这些东西都是一个。
但是我感觉是因为我学的是就比较代数结合的 toric variety，就相当于要考虑这个的 dual， 就长这个样子，这就是它的 dual， 在这个 R2 里，对吧？然后它实际上是有三个这个空组成的一个范，然后它的队友就会队友到这样，所以你必须要这个等腰才能行。然后相当于如果你不等腰的话，你相当于是要把这个东西做一个移动，你相当于是要把这根线移到这里。然后这个应该会得到另一个 toric variety，
是肯定是另一个人 toric。
对，所以我的意思就是说，如果你去改这个坐标的话，你的整个P2 就被变掉。
对，它应该不是 P2，它可能就它画出来也是这样，但是是长这样的吧？是长这样的，就在你的 dual。
对，是的。
但它好像还是 P2。
应该不是吧？
是 P2，
我感觉应该不是。
对，
我感觉应该不是。
对，我知道的例子也只有这个
P2，一个 complex surface，
可能有什么不 smooth 之类的一些东西，就是可能
我感觉是
好像有一些格点什么的。
这个应该是 smooth， 但是它有可能是 P2 blow up 一些点。对。
对，好像你要画成 fan 的时候，它好像是要这些东西里面都没有其他的点才行。要这些东西里面都没有其他那些 lattice 点。才行。
OK。
对，如果你把这个搞得很大，搞个很大的东西进去，可能
这个大小，
我的意思是，比如说你搞一个什么0、2，搞个什么3、0，然后搞个这里搞个什么负3、负2，你搞个这个toric variety 什么的，是不是这里面是有一些点？
什么是点？你的意思是整数格点？
整数格点。
那你把这个02和30同时扩大一个倍数，就可以一定有整数格点。
对，但是我们在定义这个 toric variety 的时候，是不是这3个向量要搞成一种像 minimal 的？
这个不需要，
不需要，
我感觉不需要。
对，那你这个我就完全变掉了，就因为我的理解，这个02这个就像是C2 的平方，然后这个像是一个 C1 的立方，然后这个像是一个这个分量相当于是一个C1 的负3次方及2的负2次方，所以如果你把这个都扩大一个倍数的时候，这个 mapping 这个 holomorphic map 本来也会变的，对吧？你把这个变成4次方、6次方什么，这个映射完全变掉了。虽然它也一样是 satisfy 这个 equation 是这个是比如这个 x y 这个叫 c 的话，一样 satisfy x y 的意思，但是你 parameterize 它这个用 x1 x2 parameterize 的时候，这个
我好像不太明白你说的这个东西的 setting 到底是什么，为什么会变成4次？你的意思是那个东西它的理想的生成源还是什么意思？
是就是
然后你想说的是，就是你想说的是我说的这种就是这种泛的这种情况，还是这种 polytopes？
我的意思是，我记得在这个 fan 的这个情况里面，如果有 有格点的话，它起码就是如果你
但是这个范它是无限大的，它是永远延伸出去的，就是它是没有一个。
但是你是用了一组，对，是无限大，但有一个
哦，你的意思是要找到第一个格点是吧？你要找到第一个格点，因为它有很多格点的条形。你的意思要找第一个格点？
对，
这个有什么本质性的区别？
我记得好像是不是用一和一负一，对，
其实确实会对应它的 divisor， 这个是没有问题的。
对，
但是我感觉我不知道这个本质性的区别。
我的意思，你都用3个向量的时候，
哦，
有的时候会搞出来，可能你们叫不 smooth 还是不 normal 的。
不 normal 的情况是另一个问题，就是你考虑的已经不是一个这种泛了，就是空了，你考虑的是一个半球。对，就是你考虑的是一个相当于是 lattice 切一刀，
对，
然后你才能讨论是不是 normal。就是你只要考虑泛的话，其实就相当于你做了一个 normalization。对，就是 normal 那个条件是就是非常怎么说非常 subtle，就是基本上可以考虑，就是我们考虑的都是 normal。对，就是 normalization 是一个怎么说呢？它大概相当于是在半群里头某一种取娣方的一个过程，就是应该是你的这个半群嵌入你的群化以后取个娣方。对，大概这个是 normalization。
就是你画出来一个 fan，
对，
它有一个办法是去 consider 那些
去
不 normal 的问题。
对，这个画出来一个范的意思就是包含所有格点。
OK，
对，然后不 normal 的情况下是只包含某些格点。对，大概是这么想象的，这个不 normal。
所以我们刚才讨论的是，如果你把这个东西，换一点，这个就是要用3个。
对，就是现在考虑的问题是，如果你不取这3个来，如果你取的是这个，会不会有问题？对，就不是你这种很单纯的只是变一个1，就这样的话，你就把这个给变过去。但是我是这个向量乘个2倍，然后剩下2个都是单位向。
一个向量乘2，另外2个单位向
对
量。那这个它首先不 balance 的，在我们这个条件里它不 balance。
对，是的，但是这又是另一个问题了 ，balance 的怎么说呢 ？balance 是一个向量的问题，我这里现在是个 fully total。
对，你现在是，wait，你现在这个说的是一个，你就是这个 fan 上面这个方向上面你取了一个2倍的向量，然后你生成了一个它的 dual 是叫这个 polytopes。
对，
但让我反映一下，你这个 fan 整个 fan 是这个 fan 变了吗？
不变。
fan 不变的，是不是它对应的这个？因为是不是就是用 fan 里面是不是什么补录了3个
也可能我理解的有问题，也可能不是这样，也可能就是必须要，对，也可能我理解的是不对的，我觉得可能不能这样对应的应该就得是这样的一个等压值要塞子。
对，就是你用 fan 的语言说是好像是补录了3个什么 C2 什么的。
是的。
就是每一个这个都是一个 C2，然后3个补录起来，但
是的，
把一个放大2倍，好像并不影响这个补录。就是说，在这个 fan 的语言里面，你取倍数好像是不影响的。
对，我可能不太熟这个 polytope 的语言。
对，所以你取倍数是不影响你的这个 gradient of fan。所以这个 fan 的那个生成源就像是这里这个向量，就是 fan 的这个 axis， 就这些 axis 就是这些向量。所以这个放大倍数是不影响，所以它约定了取一个最小。
OK， 你说的有道理。你说的有道理。等一下，
我一直觉得这可能是个 convention 的问题，就是这个 compactification of 这些。
看来不能这样觉得。对，你这样会造成你这个不是 normal vector， 就是你刚才表达的意思就是说，这三个向量一定得是 normal vector， 那么你就必须得取一个这样的一个。
对，必须得取这个得是垂直于这个的，就是取 这个 polytope 应该长这个样子，对，必须长这样。对，长这样。你就算放大这个2倍，这个 normal vector 不变了，你还是得这样。
对。哎，这个有点意思啊，这个
对，我也觉得这个取法应该是个 convention， 它取了个最小的，取了最近的格点。
类似一个队友剖分的操作，把我之前的面变成点，然后之前的点变成面。
它这个画的是一个 P 图，
对，
然后这个点对应的就是你原来说的那个 C 图，
对，
这个点附近的一个 local chart 它画成是个 C 图，差不多的意思。
这个跟那个 tropical 那个叫什么 tropical rain， 你那个叫什么semi
哦，对，它那个怎么搞过去的？就看最简单的那种 curve，就是 ax 加上就我不要 ax， 就 x 加 y 加上1等于0嘛。这个是一个 curve 在 C2 里面
C2，
或者 P2 C2， 就因为这里有
你还得加个 z， 如果你要在 P2，
那就 C2 啊，就是 x y 两个都是负面两个
OK
C2 OK， 然后它画出来大概是这个样，它把 C2 画成这个样子，就这个点代表负穷，就这个是负穷，然后一个方向，这个方向是 x， 这个方向是 y。反正我这有点记号有点问题，应该写一个小 x 小 y， 然后它这个你把这个大 X 当做是E 的小 x， 就把它重新参数化一下，对，然后把小 x 当做是OK， 就我这个重新写一下，然后
就是关于小 x 小 y 的方式上，
对，然后关于小 x 小 y 的方式，对，反正可能带一点 log 之类的，但是你把这个 h 趋于0的时候，这里的这些加法就会自动的变成取 maximum， 因为你可以看出来，它接近0的时候，你的这个东西数量级就是这个 x 值，所以你当这个玩意趋向于0的时候，你的这个 curve 在小 x 小 y 这个曲面里面画出来，在小 x 小 y 这个参数里面就画出来的话，就相当于是这个是 maximum 的 x 和 y 要等于负1。
有点意思。所以这个就是那个图像嘛。
对，那个图像，所以会变成一个 piecewise linear 的图像。这个加法应该对。
但这不是一个区域。
我可能这个我这个 sorry， 我这个数也不要，我画个这个好吧，加2y等于0。那它应该是这个画出来是应该是 maximum 的x， 然后这个是2加2，它对应的是y 可能是 y 加2，就是在那个普通的加法里，这个乘法是对应的普通加。还是太复杂，我说这个吧，直接 x 加 y， 它等于这个对应的 max x y 要等于这行不行？我有点 confused， sorry， 我随便瞎写讲，就 x
把
y
z 放进去更好考虑一点。你是不是应该在 CP2 里头考虑这个问题？就像他一开始写那个例子一样，那个什么，他一开始写了一个1/4骑次方程的例子。
所以你只把 z 其次座位放进去可能会好一点。
比如说你这里写成 x 加 y等于 z，
嗯，
它是一个 CP2 里头的一个。
对，但他上次说的时候是根据一个 local
啊
point
OK
来写的。然后我大致讲一下，就是这个 x 和 y 谁更大，就取哪一个。然后他要比如取固定一个一这里，就是说那你就是有可以是 x 取一，就 x 取一，但是 y 只要比一小都行的，就这个，就因为这个方向是 y，x 取一 y 比一小就行，或者是 y 取一 x 比一小就行，所以是
等一下，x 取一 y 比一小，
对，所以是这个，
那为啥是这个？
因为这是 x 是一
啊，
然后这个 y 方向，这个 x
OK，y 比一小，然后 y 是一
对，
，x 比一小，OK 是这两个，对，
然后但这里有个问题，就是这根是怎么来的？这根看上去是 x 和 y 都比一大等于一的时候，所以它应该是，好，我们来讲一个这个情况吧。那就是，所以它这个 max 是它刚才取了 x、y 和一的 maximum， 如果是一的话，不对，这个不能是。我的意思就是说，如果 x、y 都大于一的时候，它需要有一个条件是 x 等于 y。right。为什么 x 等于 y？感觉是就是这两个东西得数量级是一样的时候，它才能把这个东西消掉，变成一个比常数。不然它这个 h 很需要0的时候，这两个不一样，它一定会造成有一个是无穷大的。OK， 我看这两个如果 x 和 y 不一样大，那就是那个 x 和 y 更大的那个会 dominate 这两个的加，所以它两个得搞成一样大，因为事实上这些 x y 里面还带有那个 face 的，就带有那个 e 的 i 多少次方的那种东西，所以他们两个如果数量级，他们的radius 那个数量级，就是这个实部的数量级是一样的，你还是可以消去的。就是这两个是就其实你看着这个加法，但是因为这里面有 face 的，它里面有那个辅的那个就 x 和 y 本身是它是 complex trinomial number， 就是说它实的部分你给它除了个 h， 它本身还有辅的那个部分，所以辅的那个部分会在这个加法上面提供一个符号的，就其实是这里是有正有负可以，所以也就是说，如果这两个东西它的 radius 大小都已经不一样了，那么就是如果你 x 和 y 比较大的时候，必须要 x 和 y 相等的时候，它才能满足这个方程，就小 x 和小 y 必须要相等的才能满足这个方程。
那跟那个一有什么关系
I see， 这个其实是0。我现在搞明白，就是你这个 x 是0的时候，你这个方程才是1。OK， 就是说，你 x 如果是正的的时候，x 和 y 两个都是正的的时候，你要怎么想办法把它消掉？因为 x y 如果是负的时候，这个本身 h 取个极限基本上是
这是减号。
这里是加号，这里加号，所以这里就是加号。严格来说，这个数是这样的，就是 x 应该是要等于 e 的e 的它的实部，就是它的 x 一个实部，
左边是大 x 嘛？
大 x，就是它的实部 xr， 还有它的虚部 xi， 长成这样啊。然后我统一的除个 h 吧。
啊，这里是 x r 吗？
这个是 xr， 对，这里我都只在实部里面画，对，只在实部里面画。然后就是说你让 h 趋向于0的时候，你会面临一个问题，就是 xr 如果是小于0的，那么这个极限你 h 趋向于0的时候，这个很好，这个极限没问题。h 趋于0的时候，这个东西指数很负的时候，你这个东西基本上就是0，大 x 就会变成0。
那你虚部不变是？
虚部可以变，就是说这个我只画了实部，但是它虚部如果你 remember 它的虚部的话，它就会画成那个一个圈。
啊 ，OK， 那 h 趋于0，极限还是不存在。 但是我要把虚部都记住。
H
啊，或者我现在就理解成我 fix 一个虚部，相当于我在圈上 fix 一个点，然后我再另一个 H 区，可以啊。
然后如果 x 是正的，那这个极限取了会有问题，就你要满足这个式子，就你 x 和 y 如果同时都是正的，
就是如果 x_r 和 y_r 同时为负，
同时为负就是要么就是这样，要么就是这样。你要满足这个条件的话，你满足这个方程的话，要么就是在这根上，要么就是在这根上。
那这里是不是应该减1呀？
这里加一减一其实关系都不大，因为这里都带 face 的，这里都有负的，这里都有这里都有虚部的，其实，因为这个大 x 大 y 它都是复数。
你的1会变成什么？在这个方程里还是1吗？就1的0次方等于1嘛。
它采用的是这样一个操作，就是把它 shift 一下，大概是把这个叫做一个，把这个叫做一个新的变量。
那你要把那个1划掉那一层。
它要把一个方程先写成一个标准的这种方式，过一个点的那种方式。我们看以后，也就是它这是它这次，上次，也就是这次。它第一步是先把这个方程写成一个标准化。它先写成这个方程，就是这个加的这里面这个常数是0，就是没有这个右边是没有常数的，就是 x 减 b， 还有一个是反正写成这样标准化的方式，然后把这个 x 写成一个这种形式，它在辅的这个地方反正可能没除这个 h， 只是在实的这个地方把它重新参数化了一下，把它的指数上的实部重新参数化了一下，然后你的这个就是它刚刚这个标准的方程就会分成几个 case， 就是在你可以讨论当 h 趋向于0的时候，这个应该画成什么样的。所以当 h 趋向0的时候，它先考虑了，比如 rx 是大于 b， 所以 b 就是这个数也会有一个实部，就是这个数它写成 e 的多少次方也会有个实部，就是你先比较，比如说这个 x 和 b， 就比较 x 的实部和 b 的实部。所以如果 x 的实部是大于 b 的实部，反正分类讨论一下，它会画出来一根线，就是在这个平面里面可以画出来一根线。只有在这根线上的时候，在这些实部都满足这样一个很曲热的线的时候，它才有可能满足这个辅的方程。反正就分类讨论，这就是分类讨论，就 x 的实部是小于 b 的实部，还有这个是 y 的实部可能也是有个条件，你看啊，就是它用的是这个，它全是用 x 的实部来讨论，就相当于我们在这就是全部用的是 y 的实部和1的实部，它全用实部来讨论。
就是小于 b 等于 b 和大于 3。
对。
然后等于 b 的时候就是竖的这条线，
对。
大于的时候就是这个 x，rx 等于 ry 这个。
对。对，因为它大于 b 的时候，就是这个y 本身就 dominant， 所以你 x 和 y 这两个加起来以后要等于0，就你可以不用看这个，因为你 这个 y 如果是大于这个东西的，那这个不用看。所以 x 和 y 你比较的时候，它必须要这两个数量级要相等才能等于0，就是它的这个实部必须要相等，它才有可能。如果这个实部不相等，那这个比如说它大于它，那这个大的不得了，虽然不可能 cancel 掉。
不明白，它们不应该是一个正负数的关系，它们才能等于0。你不应该是
对，但它这里有虚部的。
但这个有什么关系？
就是你本来这个数是，比如说是 e 的很大的一个，我表示很大的一个就是很大的一个数然后这里还有加上一个辅的部分，比如说这里是个 e 的，又是一个很大的部分，然后这里加了一个，所以这两个加起来是会等于 就有一个这个虚度在这里，这个就会造成一个负一在前面。哦，上课了，哦，sorry，哦，我来上课了。OK，谢谢张同学。啊，只有一个黑板，谁在？
这是哪个学校？这是哪个学校？学校杯子。我搞环保。杯子需要买。啊。
Okay, so let's begin. Okay, so last time we have defined this Young graph, right? Okay, so the vertices of this graph are just a set of all Young diagrams, and of course arranged in levels. Okay, so namely for each level, and each level is just consists of the Young diagram with n boxes. Okay, and then this is a so the edges defined just in terms of the symmetric group, okay, that we already know coming from the representation of the field symmetric groups, okay, which at the level of Young diagram just means that okay, so you adjoin, you connect the two such Young diagrams of size n plus 1, okay, if one is obtained from the other by adding a box, okay, right. Okay. So last time we have already defined this notion, so just recall this notion. Okay. So a coherent system of distributions, okay, of probability distributions on the Young graph. So okay, so this okay, yeah. So where each probability distribution okay. Okay, so of course, yeah, so Yn is just a finite set, right? So it's just the set of all Young diagram with n boxes, right? So therefore, Mn, so i.e., so sign n lambda for each Young diagram with n boxes, and of course, Mn lambda such that the sum of these is U for 1. Okay, so that's what I mean by a probability distribution or probability measure of Yn. And coherent is the condition, okay, such that the compatibility or the coherence condition is satisfied. Of course, if n is 0, then yeah, for us it's just a convention anyway. N is 0, the 0 level just regarded as an empty diagram. Okay, so and of course, if n is 0, you just regard this number as just 1. Okay, the single number. Okay, anyway, so the coherence condition means for any positive n all Young diagram U, say level n minus 1. So we have that. So this condition being satisfied, okay, so okay, right. So this is the coherence condition. So okay, so on the left, okay, you form this sum over those lambdas. Okay, so right, that is obtained by adding one box to U. Okay, right. Then this being equal to this. Okay, we have already I've already said that this can be interpreted as a in a form in a matrix form. Okay, so recall that we say the stochastic matrix. So this is okay, this one. So this is matrix of format y n cross y n minus 1. So therefore you think of the rows as indexing the Young diagram of size n, columns as indexed by Young diagram of size n minus 1. Okay, so such that the entry for such a here, the lambda being of size n, mu of size n minus 1, this is equal to dimension of mu, both dimension of that. Then there is something of mu by adding one box and other ones. So this is a stochastic matrix, meaning that all the entries are non-negative, and if you look at each row, then the sum of all the entries of each row are equal to 1. Okay, right. So this is the condition. Then you can you can think of this coherence condition. This means it's so n times this matrix equal to n. So here we think of these m. I mean, right? You think of this as a row vector. Okay, so here you think of so if you think of right, as I said, Mn is really the range of these numbers, right? And as then ranges over the Young diagram box. You think of it as a row vector. Okay, and of course similarly for okay, yeah. So the coherence just means this condition. Okay, yeah. So as an aside, although we do not really make serious use of it, so it's certainly good to say a few words about the probabilistic motivation. So okay, yeah. So so this is just an aside. Okay, as I say, we do not really make serious use of it. Okay, but it's good to know. Okay, so so in probabilistic terms. Okay, so this family of probability distributions so determines. So here integers. It determines a family of random variables. Okay, like that. Okay, so here, okay, index. Okay. Such that lambda n x values in y with normal. What it means, okay, is simply just the form. Okay, so I myself do not work in probability theory, but yeah, I mean, if you know something, it just means this, right? So probability for lambda n to take a particular value and say lambda, okay, then this is equal to right for all. Okay, right. Okay, the coherence condition is then interpreted as so these numbers or really the entries of this matrix is interpreted as conditional probability, and so namely probability of okay, and bigger than 1 and all less than mu, okay. And size n mu of size n minus 1, then the probability or the conditional probability for lambda the n minus 1 value mu, given that the n variable lambda is equal to this. Okay. Okay, yeah. So the coherence condition, just becomes the consistency equation. Okay, that probability of saying that lambda n minus 1 random variable being mu, the probability of this event is equal to sum, right? Over all young diagonal lambda size n. Okay, conditional probability of this. Okay, conditional probability times the probability of the okay. So therefore, if you remember, you probably learned this in high school. There's something called Bayes formula, right? So this is a conditional probability for the n minus 1 random variable to be equal to mu, given the n variable to be equal to lambda. But we naturally, if you think of this as a kind of growth process, so namely that you think of n as a time, so to speak, okay, and then it's like we try to form a probabilistic model of such a for the growth of a random Young diagram, so to speak, okay. So therefore, it's more common to try to with the time going forward, okay, in their work. So in other words, you would like to say try to compute the following. So namely that n variable to be given that the n minus 1 variable to be, okay. So and of course, so by using Bayes formula. Okay, so here, say this is not zero. Okay. Okay, right. So then this is equal to so this conditional probability of the n random variable to be equal to divided by n random variable to be equal to u. Okay, right. Yeah. So therefore this is good. Times okay. Yeah. So therefore, as I say, so you're given so this conditional probability is independent of the choice of the coherent system of distributions. Okay, so the way we define it, the value only depends on lambda and mu. Okay, but given such a choice of coherent systems, then this allows us to compute these the forward time, so to speak, conditional probability. And as I said, okay, so from the probabilistic perspective, this allows us to understand it as a kind of a model of the for the growth of a random Young diagram. Okay, with this, okay, as I say, n as you think of it as a time. Okay, so the transition probability for at the n minus 1 stage to n stage is then given by this. Okay. All right, as I said, they just an aside. We do not need to make this. Okay. Then come back to with the discussion on the relation with the infinite symmetry. Okay, so this was introduced because of the following simple proposition. Okay, so firstly, recall that and so so for us, okay, actually this is the definition. Okay. Okay, normalized character. A normalized character on the infinite symmetric group. Right. Okay, so for us, this is taken to be a definition. Okay, so a normalized character where it's a function is a function, but actually it's going to be real bad. Okay, but anyway, so it's a function. Say again?
You said real value.
Yeah. Oh, okay, yeah, certainly, yeah. So, I mean, because in for this is again a special property for the time. I mean, just because this definition actually works for any G. Okay, so but for the case of the infinite symmetric group, it's actually all going to real value. So similar to something that we've seen before. So for these finite symmetric group, the value of the characters are actually all real value. Okay, yeah. Anyway, so it's a function on on G. That's fine. Okay, so so name the condition, right? So namely the constant on conjugacy class. Right. Well, that just means that time CH equal to time HG for all H. Okay. And so the value at the identity value. Okay, that's why we call it normalized. Okay. And third is the positive condition. Positive definite. Okay, right. So we call this definition what it means. So namely that for any the G1 CK in S infinity, take the say set one of set A a complex number. Okay. We have this quantity Okay, that this quantity is a real number and it's actually non-negative.
I have a
Yeah.
question
Yeah.
about the probability.
Yeah.
Last time you explained
Yeah.
that it's not so easy to produce.
Oh yeah, certainly.
Systems.
Exactly.
Is the
Yeah.
probability viewpoint useful to say?
Oh,
something?
well, actually, that's the point. You use these to give such an example of probabilistic models. That's exactly the point. So as I say, indeed, it's not easy. I mean, of course, as I've said, okay, as we have seen last time, so for the Fancherel measure, we have this very canonical example. Fancherel. Right, so you just make the computation, you see this is an example. Okay, I should really give this example. Okay. So, but it says, yeah, okay. So this of course gives lambda is a thing from you. I'm getting one. So this is indeed not easy to give more example. In fact, we're going to see, okay, maybe in a few weeks, okay, so a classification theory, okay, so yeah, but it's indeed not a non-trivial matter, okay.
So there's a classification actually.
Yeah. So what you could still remember. So last time I wrote down some complicated formulas. Okay. So and for a family of such distributions. So roughly speaking, so the classification theorem is that the most general construction is obtained by certain averaging of those distributions that I have written last time. Okay. So that indeed is the Virchow-Karoff theorem. Okay, and we will come to that maybe in a few weeks. But certainly we need some preparation. Okay, so actually maybe I should say okay. Okay, I should add one more condition. Okay, so this condition, so namely is that okay, yeah, so one more. Okay, this condition. Alright, so this is a positive definite condition. Now, so easy to see then that if I is such a is such a normalized character. On infinity, then if you restrict it to each of the finite level, then chi n, okay, then for each so I sub n, which is just I restrict as n, symmetrical n. Well, okay, of the numbers of 1 to n, where we say normalized character on this. Okay, because the condition just remain the same, right? But we have seen before, okay, in the first few lectures, right, of this course, okay, so that any normalized character on a finite group, actually not, it works even for any finite group, but in particular for Sn, okay, so chi sub n, okay, another restriction of chi of Sn is can always be written as a convex linear combination of the normalized irreducible character of a group, okay, which is Sn in this case, okay. So therefore, that means that we can write chi sub n, and of course we know that the normalized irreducible character, okay, I mean, of Sn parameterized by partitions of n or Young diagram size n. Okay, right? So hence we have it can also be written as form with these mn lambdas are all non-negative. Sum, okay, it's a convex combination, meaning that the sum of these coefficients equal to 1. Okay. Now, of course, so the coherence condition comes from the fact that these chi-n's all come from the single chi. Okay, so in other words, when you restrict chi-n further down to say the level n minus 1, then you have to have the compatibility, right, with the corresponding form at the level n minus 1. Okay, and that is exactly where the coherence condition. Okay, so but since I submit when you further down restrict to the symmetric group of size n minus 1, well, then it has to be equal to restrict to n minus 1. So if you write out explicitly what it means, so explicitly, okay, so you take this formula. And then so and this character, right, which is the group character on Sn, but you restrict to S of n minus 1. This has to be equal to the corresponding formula at the level n minus 1. All right. Okay. We know the branching rule, right? So, but branching rule. Okay. So, which we are learned before, the character chi lambda, which is a character on the Sn, when you restrict to S of n minus 1, this is then equal to the sum of the characters. Individual characters parameterized by those views. Okay, mu is of size n minus 1, and such that mu and lambda differ by 1. Okay. By particular rule, yeah. So you're substituting this, so substituting. Okay, so making the substitution. Right, so you can make the substitution, then the left hand side becomes following. So sum over lambda size n, and then sum over those view of size n minus 1. View and lambda differ by 1 box, and then view over lambda times view over view. Right? And you can rewrite it as the outer sum now is over those views of size n minus 1, right? And then inner sum is over those lambda of size n, and of course lambda and view differ by 1 box, okay? Right? And then So when you compare with the right hand side, right, remembering that the characters are linear independent, right? Okay, so therefore you compare with the right hand side. Okay, so compare characters with so we obtain the coherence, exactly the coherent condition. Okay. And conversely, so this is something again, you just run the computations backward. Okay, so conversely, if so this is leave it to you as an exercise. Okay, but as I say, you just basically run the computations back. Okay, so if it's a coherent system of distribution. Distributions on the target graph y, then by defining the function I n on Sn by okay by the same form. So namely I n equal to some lambda n boxes, okay, and then so normalized character lambda divided by lambda. Then these kind lambdas are compatible. Okay, then I restrict to s of n minus 1 I on and hence if rise to if rise if a normalized character time of S infinity. Okay. Okay, such that time restrict to being for just means that these chi-n's are compatible. Okay, so therefore you can define unambiguously, okay, the corresponding function kind on the whole on the infinite symmetry. Okay, and so this so corollary, okay, is there of this computation is that this is the bijection. Bijection, okay, between the normalized of S infinity and the Fourier system of distributions of profit distributions on the Young graph. Okay, and furthermore, this bijection preserves the convex. Preserve the convex. Okay. What it means? Okay, so because obviously, right? So both these two sets has a convex structure. Okay, so I mean in the usual sense, right? So you have say two elements in either of the such sets. Okay, you can define the line segment. Okay, and all the points on the line segment between these 2 points. Okay, so convex just means that okay, that every point on that line segment is still in that set. Okay, and so by saying, I mean, just means that this bijection, okay, between this normalized character S infinity, right, and the distributions, coincidence of distribution on the Young graph preserve this convex structure. I mean, that should be clear because we, from the explicit way, we give such a bijection. Okay. But as I have kind of mentioned before, so these convex sets are huge. Okay, they're infinite dimension. Okay, so therefore, as you're going to see, we're going to need some functional analysis to understand this more precisely the theorem of Shortcake in order to understand the situation properly. Okay, so let's see which I should erase. Okay, okay, now so at this point, so therefore it's also good to state the theorem of Thoma, which we're going to certainly prove it by following Bershik and Carroll. Okay, so let's see. Okay, I put nice there. Okay, so now it's the Thoma theorem. Okay, so firstly a definition. So a normalized character. Okay, so for us, okay, the character on S infinity is always going to be normalized. So sometimes we to state right things, just say a character. But anyway, the normalized character on S infinity is more extreme. Extreme. Okay, if it is an extreme point. In the convex set of all characters, normalized characters of S infinity. Okay, yeah. Well, what does it mean? So, i.e., it is not the interior point of a line segment in the convex set. Okay, so this is a general definition. Okay, so for any convex set, okay, so a extreme point just means that it is not a interior point in the of a line segment in the convex set. So of course, if you are in the finite dimensional situation, okay, so let's say like so like if you're in the finite dimensional situation, right? So okay. Yeah, okay. Okay. So if you're finite dimension, I mean including the boundary, okay. So in this picture, the boundary is included. Okay. So then what are the extreme points, right? Then exactly these corner points, right? That's also why we call it extreme. So in the finite dimension, so and but in the infinite dimensional case, it's much more careful. One has to be much more careful, and also as you're going to see, okay. So Thomas' theorem exactly gives a complete list of all the extreme characters of the S infinity. So of course, again, by the same token, if you are in the finite group situation, right? So for finite group, then the extreme points of extreme characters are nothing but the irreducible or normalized irreducible characters. Okay, by the same token, because as we have seen, right? So if you're in the finite group situation, a normalized character on the finite group is a finite convex linear combination of the irreducible characters, right? So therefore, I mean, the picture is really again just same, okay, with these convex points corresponding to the irreducible character. So the extreme characters, so correspond to the irreducible character. So therefore, for us, okay, so we also at this momentarily, you can say we take the extreme character as a analog of the irreducible characters. Okay. Yeah. So even though at this point we refrain from talking about representations of this group, okay, which is I mean there's some technical difficulty, but it could be overcome. But it is a bit easier just to work with the characters at this point. Okay. So therefore, even though we did not talk about representation of this group, okay, but nevertheless we are able to talk about these extreme characters, which as I say, okay, it should be thought of as analog of irreducible characters, okay, for this group. Now, the theorem of Thoma can give a complete classification of the extreme characters of the group infinity. So, which is related to those formulas that I have written last time. Okay. Okay, so let's first we define the Thomas simplex. I think I already did it last time, but again, just to recall. So omega, okay, so this is a subset of the product of two copies of the Q. In other words, constantly matching copies of the interval 0, 1. Okay, so in other words, omega is a set will consist of pairs alpha and beta. Okay, okay, so alpha and beta. So these are called Thoma parameters. Okay, and each of alpha and betas, well, okay, they are yeah. So sequence of numbers in the interval 0, 1, but they are all in the decreasing order. So alpha consists of tuples. I mean these are infinite tuples, alpha 1, alpha 2, and they are all decreasing. Okay, and of course they are all between 0 and 1. Okay, and similar for beta. And such that, and also the condition that the sum of these ordinals are okay, so this is the condition. So okay, omega is called the Thoma simplex. So omega is actually a complex metric space. Okay, so if you remember your undergraduate concept topology, you recall Tikhonov theorem, right? So namely that 0, 1, the interval 0, 1 is proper compact. Okay, so you take the product of I mean this is with the product topology, right? I mean the product counted many copies of 0. So this is again compact by Tikhonov theorem. Okay, and in fact, not so hard to show this is omega. I mean, with the defining condition given by this, omega is closed in the right hand side. So therefore, omega itself is also compact. Okay, so of course it's infinite dimensional. Okay, so now the Thomas theorem is called Thomas theorem. So the extreme characters so the extreme characters of characters of infinity given of classified by the okay, so namely, in fact, there's a following explicit formula. So namely that in fact given data, okay, alpha beta with so the corresponding main character is given by okay. Okay, let me write it down. Okay, okay. So if so, of course, this is going to a function on S infinity. Okay, and context I've got being a character is really a class function, right? So namely, you don't need to specify the value for a conjugate class. Okay, but anyway, so if sigma is S infinity with cycle structure, I'll explain what it means. I mean, essentially the same as the finite group situation. Okay, so with cycle structure, and say with row of the form. Yeah, 3 okay, so this means 2 repeated m2 number of times, 3 repeated m3 number of times. I just explained, but anyway, let me first write down form. This then is given by form.
If it's row inventory was a natural number or prime number.
So, say again.
I mean, row was enumerates the numbers, let's say 2 to the m2, 3 to the m3, or
I explain. It actually just it's just actually just a finite okay.
oh, so it's not like
It's really just a really just row is really a finite time.
oh, it's not like the next element was 4 rather than 5. For
No, it's the same kind of notation that I've used before. When I write this, okay, so it means that say right. So the 2 okay occur as one of the rows. Okay. And probably this occur a number of times, and by m2 it means a number of times.
okay.
2 occur as a row, and similar for 3. Okay. So anyway, so let me first write down a form like that, and then I take a break, okay, and then I explain these more completely. Okay, right. This is the form. And of course, this is the right hand side is really a finite product. Because mk is the row for k sufficiently large. Because as I say, okay, row, you think of row is really just a finite, it's really just a finite, it's just a finite. Okay. So although I write this, okay, this form, but mk is for k sufficiently large. Okay, so this product is really just a finite product, even though I write such a full thing. Okay, but anyway, so that this is a form. Okay, so let me explain first, and then let us take a break first, and then I come back to finish saying some of these things. Okay. actually, so for the representative field, one need to use the Gelfand pair. So for the yeah. So so is the for just a carrot actually when you want to work with a single copy of text is it seems that they need to use the so-called polynomial factors, and I don't know anything at all. So but in terms of when we work with the Gelfand pair, K of course being just a target, then everything essentially just works as in the usual setting. Okay, so yeah, so in fact Olshansky worked in this setting. So namely, such a character, extreme character correspond to a irreducible spherical representation, like this Gelfand pair.
I see.
But you know, I mean, these things, there are not much examples of these things. So besides the infinite symmetry group, you can do similar thing for this these class. I mean, the families of classical groups, but not much more.
And in the finite setting between GN and symmetry.
Yeah. That actually is a very interesting question, but I think they do not have a definitive answer. So, well, naturally, so namely you fix a Q, and then with n varies. Okay, but it turns out that it's not this is not well, even if we work with Gelfand, okay, so this simply is not a good choice. They say that this is too big, okay, so to speak. So somehow they work with a let me think what that actually is. They cut and they work actually with a certain subgroup of this. Okay, it kind of looks like this. And then yeah, so it kind of works like this. So namely it works with maybe a certain chord B. Okay, so B is this. So it's not really the Borel. Okay, but
These groups that occur in the.
this is but the point is that this part is it has to be fine.
Yeah.
Yes. Okay. And of course this block could be okay. But this block has to be fine. So somehow they look at what these the analog of the finite classical groups ought to be in this case. So somehow they have and then there's the relation with the Hall-Littlewood polynomial. So instead of the Schur polynomial that we have been talking about, so in place of Schur polynomial, so in this case so those are replaced by the so-called Hall-Littlewood polynomial. So that again is kind of interesting. So somehow you know, these things ultimately goes back to these very classical combinatorics. Yeah. So
With GN and C, you can consider the limit also, or.
You just need to do the compact integral. If you want to work with the Lie group case, just take the compact integral.
And then there's some version of Schrödinger duality also.
Yes. Okay. You can do some version of that. Okay. So for instance, say instead of the Schur this Young graph, okay, there's some modified version they call it Schur-Bar graph. Okay, essentially, as you say, kind of incorporating the Schur-Bar duality with that. Okay, in that kind of setting. But you mean Schur-Bar duality between this and this?
Yeah, between this.
No, then that seems to be more complicated. Yeah, it's not that clear what it means in this case. Okay, yeah.
So it has not been looked at, or it's just that formulation is unclear.
I don't know. I mean, maybe it's not clear how to do that. Okay. Of course, I mean you know, I mean at the final level, there's this already an interesting connection, right? So they need the Kazakh map. I mean, Frobenius identity. So these are the irreducible characters of finite symmetric group, parameterized lambda. Another characteristic map is S lambda, right? But S lambda, we know this is the by the bound formula. We know this is the character of the irreducible representation of the compact unitary group parameterized by lambda, right? So somehow at the finite level you have this, okay, but at the infinite level, it seems you don't see this though. Okay, so it's not clear what is the direct relation between these things. Okay, yeah. So let me continue. So just add some more remark. Okay. So firstly, in the definition of this Thomas simplex. Okay. So then. Okay, so in fact, so I make the remark that omega is actually closed in the right hand side. In fact, let me say the following. So in fact, so remark. Okay, so the function, but some k have to be okay. So the function say on omega divided by yeah. So if you have okay, so such a common parameter omega, okay, right? So goes to sum of these things, sum of the coordinates. So this is actually not continuous, but it's only lower semi-continuous. Okay, it's not continuous. Okay, but lower semi-continuous. Okay, so therefore, some care has to be taken when we work with this so-called Thomas simplex. Okay, so indeed, if we define this subset omega naught, okay, so be those Thomas parameters omega such that the sum of these coordinates equal to 1. Sum is equal to 1. Then omega naught is actually dense in omega. Then in omega. Okay. So this is again something that has to be one has to be careful when one works in infinite dimension, right? So because it's say if you're in the finite dimensional setting, right? So right? I mean, imagine so instead of omega, this is just a finite sum, right? Then this omega naught, right? It corresponds to a certainly part of the boundary of omega, right? So it could not be certain, it could not be dense, right? But in the infinite dimension setting, actually it's dense. So if you like, you can take it as an exercise. Let me just illustrate with the following. Right, just an illustration. Okay, that's of course also illustrate why this function could not be continuous. Okay, because this omega naught is dense, right? And this function, when you evaluate it at omega naught, is just constantly equal to 1. Okay, yeah. So this could not be continuous. Okay, but it's not hard to check that is so-called lower semi-continuous. Okay, so anyway, so let me just illustrate why omega naught is actually dense. For instance, say you just consider omega to be the point where all the coordinates are just 0. Okay, right? So this is of course in omega, but not in omega naught. But you can approximate it by a sequence of points in omega naught. Sequence of points. Where omega n, right? Okay, it just consists of the points 1 over n, the dot 1 over n. Okay, and then the beta just is of course the n. Right. So now you see immediately that in the product topology, omega n then converges to this, okay, as n tends to infinity. Okay, right. And of course these things are in omega naught, right? The sum of the parameters are equal to 1. Okay. Yeah. So therefore, in the infinite dimension setting, as I say, so sometimes the intuition has to be one has to be more careful. Okay, some of the intuition in finite dimensional case can be wrong. Okay, yeah. Okay, and okay. So another remark concerning this Thomas formula, namely this. So, so another remark. So, which is just a simple exercise. Okay. So, the remark. So recall that for finite symmetric group, okay, then the conjugate classes. Just try additions of n, okay, or in other words, again, just as additions of n or Young diagonal functions. So, for example, okay, so the identity elements. Okay, E of f corresponds to trivial. I mean the conjugate class of the identity element. Okay, so in that case, it just one repeated itself n times. Okay, right? Because in terms of the cycle decomposition, the identity element just means that maybe in our convention that Sn acts on the integers from 1 to n. So the identity element just means that each number is a single orbit, right? Okay. So therefore, in terms of the cycle decomposition, right? So it's just a product, right? Of these things. And of course, each of these is just an identity element. But from the way we make this parametrization of the conjugate classes, okay? So the identity element just correspond to this, right? As I say, each of these is just really just an identity element. But in terms of cycle structure, okay, is this, okay? So in other words, the partition is just one repeated itself n times. So in terms of the Young diagonal, just the okay, you have you only need it's an n row with each row only one box, okay, or in other words, just a single column. Okay. All right, okay. Now, so for n infinity, the picture is actually similar, except really this issue. Okay, so you can already see, right? So if n is now infinite, okay, so it does not really make sense, okay, to assign this, right, with as a cycle structure to the identity element, right? It just means one repeated infinite many times. Okay, so the solution is that you simply ignore ignore whenever one occurs as a part of the okay. In other words, let me. Okay, so for S infinity, we then have the following. Okay, so this is the opposition, which is just a simple, just a simple, namely the conjugate classes. S infinity. I'm going to try to find. Difference. Okay, so i.e. with no parts equal to 1. With no parts equal. So the identity element then corresponds to the infinity partition. Okay, so this is just a simple exercise, really. Okay, so because after all, an element of S infinity we know is, by definition, it belongs to Sn for some n, okay? And of course, we know that a conjugate class in any finite symmetric group parameterized by, in the finite symmetric group Sn, as I say, parameterized by partitions of n. Okay, so what one do, as I just said, okay, so is that for S infinity, we just ignore or pick out those parts with equal to 1. Okay, so whenever you see 1 occur, you just ignore it, you just delete it. Okay, and then by definition, the resulting partition with no parts equal to 1 is equal to the partition correspond to the conjugate class of S infinity. Okay. Okay, yeah. So that's also the one we need by here when we state Thomas form. So namely, if given an element sigma in S infinity, so the corresponding conjugate class. Okay, actually I should say, yeah, if sigma is infinity, whose conjugate class has cycle structure. Cycle structure rho. Okay, so namely the rho is the, as in here, so it's the partition, okay, correspond to this conjugate class. So therefore here it just means, so in this partition, so 2 occurs, because as I said, there's no 1, okay, so therefore there's no 1, okay, you don't have any pass equal to 1, so therefore it means 2 occurs M2 times 3 occurs M3 times 2. Okay. And of course, this is a finite Young diagram. Okay, yeah. So therefore, this mk is 0 for k larger. Okay, yeah. So then this is the form given by Tom. Okay. So maybe just drop a remark. Okay, that's also one of the reasons why this subject is has a name called asymptotic representative theory. Vershik and Gary call this asymptotic representative theory. So the reason is that, as far as I understand, is that you see, okay, so they you are able to write down an explicit formula for these extreme characters. Okay, this is really a very explicit formula. Now, if you are in the finite situation, right? Even for finite groups, for these finite symmetric groups, it's not a. I mean, one could not really write down an explicit formula for the irreducible character, so to speak. Okay, so I mean, of course, we know the condition that characterizes these characters. We've seen, right? So Frobenius identity characterizes. I mean, is characterize the character parameterized by partition lambda of n in terms of the corresponding Schur function, okay, or Schur polynomial. But it's not really an explicit form. Okay. So at the finite level, one cannot write down explicit formula, but at the infinite level, one can give an explicit formula for these extreme characters. So it is somewhat analogous to, say, when you do these special functions, right? So the special functions for the asymptotics, they usually could be expressed in terms of elementary functions, even though you don't have a explicit formula, okay, for at the finite region. Okay, so in a sense, this is similar to that. Okay, so in fact, later we'll in fact prove a more precise theorem along this direction. Okay, so namely, you really see that these are really arise as the asymptotics of the normalized character at the finite level. Therefore this is more than just an analogy. You can really understand this as asymptotics of the normalized characters at the finite level. Okay, so that's why they call these asymptotic representative theory. So we'll prove these following version. So we will prove Thomas theorem. In fact, they did is, so in fact, they show the following. In fact, and this is of course going to be the main result in the first part of this course. Main result. This course. So maybe we give a complete classification of all the normalized characters of X infinity. So these are the extreme characters, okay? In other words, the set of extreme points in the set of all normalized characters, okay? So Version and Carroll in fact prove the following, okay? So the following theorem. So this is is the convex functions. So between the following two sets, the normalized characters of S infinity. And the covariant measures on the Thomas field. So here, when we say covariant measure, we just always understood to be Borel covariant measures. Okay, so if you remember your measure theory, so when we say a measure space, you need to specify the sigma algebra. Right? So here we just take the sigma algebra to be the Borel sigma algebra. Okay. So in other words, the measurable set being the Borel measurable set, or in other words, the sigma algebra generated by open set. Okay, anyway, covariant measure. Covariant measure just means a measure such that the max of the space is just one. Okay, on the sequence. And of course, we need to tell us say what the projection is, okay, and given by the following, given, let me only put the one direction, okay, so of course we will prove it later, okay, but at least in the one direction is follows, okay, at least one direction. So let's say you're given a point measure on omega, so given a point measure, say T of omega, and the corresponding parameter. On this character. That's infinity. Okay, so right, so the value and say evaluated and any element sigma of S infinity is equal to. Okay, so I still have this formula. Okay, so the formula for the extreme characters. Okay, and of course these are parameterized by points omega in the top class. Okay, and so here, so this is then regarded as a kernel function. Okay, so we integrate these values over omega with respect to this program measure P. Okay, right. So this is different. Right, this is from Thomas formula. Okay. Now, of course, here this is sigma in S. So, in fact, it's as we're going to see. So this is this looks like a Poisson integral form. Okay, so well, I myself is not expert on harmonic functions, but anyway, so yeah, so roughly speaking, right? So if you have a say in the finite dimensional case, you have a finite region, okay, and you have a harmonic function on that region, okay, then the Poisson integral formula is a integral formula for the value of the harmonic function in terms of the value of the harmonic function at the boundary, okay, and respect to a certain point measure on the boundary. Okay, so this is actually looks like that. Okay, and in fact, this is not just an analogy. In fact, we're really going to use it. Okay. Okay, because the proof of this goes through these following bijections. That okay, so namely that right, we have already seen that the normalized character of S infinity, right, is a one bijection coherent system of distributions. Probably distributions. Okay, this is already known. So therefore, the Virchow-Kirov theorem, which, as I say, is in particular as a corollary, gives the Thomas theorem. So for us, okay, so you need to establish, okay, so what is that? So So it's these are classified, okay, by almost by the same type of form, by the probability measures on the Thomas probability measures on the okay, yeah. And as we're going to also see very soon, okay, there's also an easy bijection. Okay, I probably going to do it maybe in a few minutes. Okay, so the coherent system of distribution on the Young graph can also be understood. Okay, in terms of the so-called well, okay, so non-negative. Yeah, okay, normalized non-negative harmonic functions. Normalized non-negative harmonic functions on the Young graph. Harmonic functions. Of course, I define this, and this bijection actually is easy. Okay, yeah. But anyway, so therefore, what Vershik and Karov shows, okay, is indeed in really interpreting this as a Poisson integral formula. Okay, so not just as an analogy. Okay, so namely that so here omega, so omega is interpreted as the Poisson function as a bound of the Young graph. Okay, in the setting of a Poisson integral formula. Okay, yeah. So again, this is a kind of very interesting perspective. Okay, so by the way, Okenkopf is here, right? So in fact, some of his early works are also on this kind of thing. So a interesting phenomenon is this. Okay, so you remember I've drawn these pictures, right, for a portion of the Young graph. Okay, you can imagine that it's going to be becoming more and more complicated as the level becomes large. Okay, so but in any case, it's still just a combinatorial object raising. Okay, so now from the perspective of doing harmonic or function theory, so we can also interpret the complexity in terms of the boundary. Okay, in the sense of a Poisson integral formula. So therefore, very consistent, is kind of consistent that the boundary also it becomes complicated in the sense that it's infinite dimension. I erase it, right? So right, again, kind of defying the usual common sense. Right? So say in a finite dimensional, if you are in a finite dimensional object, okay, so the boundary has a lower dimension, so to speak. Now here it's just a graph, okay? If you like, you can say a graph is just a one-dimensional object, right? So, but it's a very complicated, no doubt about that. And then the boundary, in the sense of harmonic function theory, becomes infinite dimension. Okay, yeah, omega is now infinite dimension. Okay, and it is exactly you need to have omega infinite dimension to support this bijection. Okay, given in terms of a Poisson integral form. Okay, so this is another perspective that is quite different from what we usually expect in the finite dimensional situation. Okay, right. Okay, so these are just the comments. So now I can finally what time do I have? Okay, so let me say one more word. Okay, just to relate back to what I okay, yeah, okay. So let me do this. Okay, project easy. So how is it? Yeah. Okay, so let's just give the definition. Okay, so. Okay, yeah, so definition. So a function psi on the Young graph. Well, okay, so on the vertex set of the Young graph. Okay, which means that there's a function on the set of all Young diagrams. Okay, including the empty diagram. Okay, and a function psi on the vertex of the Young graph is said to be harmonic. If, okay, so this condition is if for any Young diagram, okay, we have psi divided mu equal to sum psi divided by lambda, where lambda ranges over those diagrams that is obtained from mu by adding one box. Okay. All right. Okay. So you know the reason for this is because this is a kind of like a discrete or graph analog of the Laplacian. Okay. So if you like, okay, if you I mean actually better to think of remove this term. You know, I mean, mu. I mean, I mean, the analogy is not perfect, but anyway, so usually when you have a graph situation, okay, so the Laplacian, right, so for a function, evaluate point means you sum over those values of functions at those vertices that emanate from your given point, okay, so it's roughly speaking, this has some kind of similarity, but I admit this is not a really perfect analogy. But just to say that there's some similarity with the Laplacian for in the usual graph theory. Okay, but this is just definition. Okay. So of course, at the end, the coherence condition just means so. Right, so the coherence condition before just means that just means that the function psi defined by this okay, you just define by the dimension. Okay, so the coherent condition before just means that this is satisfies the harmonic condition. Harmonic. All right. Okay. Okay, so therefore now it's clear. Then so n is set up a line vector. Again, okay, between the following so coherent of distribution on the graph. And so non-negative harmonic function. Of okay. Then takes the value of 1. The value 1 is the root vertex. So we have the zeroth level. Okay. And that's what I mean when I say this normalized here. Okay. Normalized non-negative harmonic functions are Y. Okay. The normalization just means that it takes the value 1 at the root vertex. Okay. So and of course this bijection also preserves the convex structure because it's again easy to see that both sets are really convex sets, and this bijection also preserves preserving the convex. Okay, so this bijection, as I have said, okay, so one direction, both directions easy, but one direction is ratio. So namely that if you have a coherent system of distributions, okay, namely these are MNs, then defining psi by this formula, okay, you just normalize, you just divide by the dimension of lambda. Okay, when you evaluate it at a Young diagram lambda at the nth level, then the coherence condition exactly boils down to the harmonicity condition. And of course, by definition, these numbers are all non-negative. Okay, so and hence the values of psi are all non-negative. And at the root vertex, namely when n is 0, then the normalization condition, then everything is just 1. Okay, so therefore you have this. And conversely, say if you have such a thing, okay, namely a non-negative harmonic function that is normalized, in other words, you take the value 1 at the root vertex, okay, then okay, so one direction is, as I said, one direction is already shown. Right? So converse. So therefore, if you are given such a harmonic function, so given such a harmonic function, such a harmonic function, okay, which is a negative and normalized, namely that psi evaluated the vertex being 1, then you just define n of lambda being equal to, just rewrite the formula, so dimension of lambda, and of course here for any n or any lambda at the n level, okay, then you just then of course as I said, okay, then the harmonicity, then of course these are all harmonic, okay, and harmonicity of course just gives the coherence condition. And you only need to show that each of these mn lambdas is a probability measure, a probability distribution at the nth level. In other words, sum of these things over the Young diagram's lambda size n is equal to 1. Okay, so you only need to show or remain to show is numbers of this dimension lambda over Young diagonal n box. Okay, it will okay, but you just easily show by okay, so indeed, you do indeed just reduction. Now, of course, the zero step of the induction is using the normalized condition and the value at the frequency of time something one. Okay, so you just do a induction. I mean, induction argument. Say you know this assumption at the level n minus one. Okay, so this assertion being true at the level n minus 1 up view. Okay, and then you use the harmonic condition. Okay, this harmonic setting. Okay, so therefore this is equal to sum over u of level n minus 1. Yeah. Okay, so dimension u sum over time where lambda is of level. Okay, if view by any box, okay, and of course you can now rewrite this, right, in this form, outer something over lambda, n boxes, and then sum over dimension u, mu being level n minus 1, mu different from lambda, adding one box, sum over this, time. Right? But by branching rule, this thing is just equal to dimension, right? This is my okay. So therefore, okay. So therefore, this gives, as I say, so it's an easy projection between the coherent system of distributions on y and the non-negative harmonic functions on y that takes a value 1 at the root vertex. Okay, so therefore the proof given by Virchow-Carol and is now now you can forget everything about the infinite symmetry. So yeah, so in mathematics sometimes they say you start from the object, okay, given by the infinite symmetric group, but now you can forget it. Okay, so now what plays the role is the Young graph. Okay, with these or more precisely function theory on the Young graph. Okay, so we would like to show that these you either think in terms of the harmonic function or in terms of this coherent system of probability distribution on the Young graph, right? So now we want to show that these could be classified, as I say, in the form of a Poisson integral representation. So namely, we want to show that they can all, now we want to show, as I said, given by Virchow-Carol, that they are classified by probability measures of the on the top state. All right. So that is then this will be the as I say the main part the theory. Okay. So let's see. Okay, let me say one more thing and then we continue after the May 1st online. Okay, so let me say one more thing. Okay. Yeah, okay, yeah, So just to round up with what I had written last time. So okay, so recall that this is what we have just seen in the previous lecture. Okay. So namely that the relation between given the normalized on x infinity, then corresponding system of metrics probability distributions on number of is given by this recipe. Okay, so namely you restrict I to each of the finite level. Okay, then as I've said, okay, it could be expressed as a convex combination of the normalized irreducible characters of the set, okay, which classifies by these lambdas at the nth level. Okay, so all right. Okay. And so now, in terms of okay, firstly, so now we have seen that in the Thomas theorem, right? So he gave an explicit formula for those extreme characters. Okay, so therefore, you would have the corresponding formula for these extreme elements. Okay, namely the extreme coherent system of distribution, so to speak. Okay, so from Thomas formula. For the extreme characteristic. Okay, so here we see Thomas signal. So we corresponding formula. For so these again with this subscript omega. Okay, so this we can say these are the extreme coherent system of distributions. One. Okay. The same thing because as I've said, okay, because the bijection preserves the convex structure, right? So therefore it just means that this is again an extreme point in the convex set of all coherent system of distributions on the Young graph. Okay, so so the extreme character chi omega then correspond to extreme coherent system of distributions. Okay, and the formula given by Thoma for these extreme character then translate into the corresponding formula for this extreme coherent system. Okay, so the formula is really just I have written last week. Okay, let me repeat again. So these given that. Okay. Okay, so I will give you the details. Okay, the how to deduce is okay given because I'm very short. So let me just okay. So given by the simple n all young time nth level. Okay, so then this distribution at nth level evaluated the Young diagram lambda. of size n is then equal to right, this again this vector dimension of lambda times this quantity, which they denoted is this way. So where this is okay. So as a notation suggests, it's similar to the Schur function. Okay, in fact, it's as we're going to see, it arises as the value of the how should I say? Okay, so I will do the detail, but there's a map from this algebra of symmetric functions to the functions, continuous functions on the Thomas simplex. I will do it next time. Okay, so given any f, okay, the image of f under this map is then noted as f naught. Okay, so this is actually an algebra. Okay, so therefore for us, okay, so you have this S lambda, the Schur function. Here, you just denote the image of S lambda under this map as S lambda, and then evaluated at omega. Okay, equal to, and it could also be computed in terms of Jacobi-Trudi formula, as I have written before. Okay, so where? So here, these H are again arises from the image of those complete homogeneous symmetric functions under this algebra. Right, so as I was saying, you have these S lambda X evaluated. I mean, under this algebra homomorphism, become S lambda naught. We also have these complete homogeneous symmetric functions, right, with index k. So under this algebra homomorphism, k. Okay, so this algebra homomorphism is actually determined by the following condition, namely that again, this is something that I have written before. So these complete homogeneous functions, okay, right? When you under this algebra homomorphism, so they become functions here on omega on Thomas simplex. Okay, these values, okay, when you package them in terms of a form power series, is given by this. Okay. Okay, so of course, I mean, there is some calculation I will do next. Okay, you see why this formula comes up from the Thomas form. Okay, so here gamma is this number 1 minus sum of these. Okay, and of course here omega form such as right? You see, if you just look at the denominator, right, and if it has the form of the generating function of the complete homogeneous symmetric functions. Okay, so I will show you next time why this form shows up. Okay, but in any case, so in terms of the system of distributions, then it is given in this form. Okay. So these formulas are as I say, okay, so you're going to see, okay, so this comes Thomas form. Okay, so I think yeah. So next, remember, so we next lecture is on the 9th because of the holiday. Okay, so the next lecture is on 9th of May. Okay, Saturday. Okay, yeah. Oh, I think yeah. So let's yeah. 9th, right? Is it 9th? Saturday, right? Yeah, because there's this makeup class for the holiday, right? All right. Okay. Oh, I want to also say because this is quite complicated indeed. So we will use a simpler model. There's a toy model, and I will also do it maybe in 2 weeks or so. That's the Pascal graph. That is simpler. Okay, and also you're going to see the basic structure of the argument. Okay, so the Pascal graph is just this graph. It's that everyone, every high school student. Just this one. Okay, yeah. And because we are now running these logic seminar. Now the Pascal graph has a very particular feature. If you look at the path space, okay, so as I have already illustrated before, this is closely related to understanding a path in the Young graph, right? Now, which is very complicated, okay? For the Pascal graph, the half space is just the so-called Cantor space, pseudo omega, right? Yeah, and you guys should recognize, right? So in logic or in computability theory, so the Cantor space plays a very important role. Okay, so somehow for the Pascal graph, okay, which as I say really just a toy model, it has a simpler feature that the path has a product structure, and in fact they call it Cantor space. Okay, but for the Young graph, there certainly is. You don't have this simplification, so that's why you have to go through a different type of argument. Okay, so but in the Pascal graph case, okay, although one can argue in a more elementary manner, but they essentially adapt the argument to the Pascal graph case as a toy model. So just to see the main feature of the argument, okay, which is more complicated than what it really needs to be. Okay, but then once we understood the Pascal graph case, then essentially the same argument just go through without much difference for the Young. So anyway, yeah. So yeah. So we see you next time. Okay. I mean the time. Yes, yeah.
知道所以我才讲。这个知道我无法判断哪个地方的人。